Section 1. Opening and Cultural Legacy of Ganymede. In the frozen reaches of the outer solar system, orbiting a giant planet of swirling storms and ancient mysteries, there exists a moon so large it dwarfs the planet Mercury. This is Ganymede, a world that has captured human imagination since the moment Galileo first glimpsed it through his humble telescope over 4 centuries ago. Tonight we journey to this distant realm together. Long before spacecraft ventured into the darkness between worlds, long before telescopes revealed the true nature of wandering stars, the name Ganymede belonged to a beautiful young prince in ancient Greek mythology. His story has echoed through the centuries, passed down through generations of storytellers, artists, and poets. According to the ancient tales, Ganymede was a Trojan prince, the son of King Tros, from whom the legendary city of Troy took its name. The myths describe him as the most beautiful of all mortal youths, a young man whose physical perfection caught the attention of the gods themselves. Zeus, the king of the Olympian gods, became so enamoured with Ganymede's beauty that he transformed himself into a great eagle. In this majestic form, the ruler of the heavens descended from Mount Olympus and swept the young prince away from the slopes of Mount Ida, where Ganymede had been tending his father's flocks. The eagle carried the youth up through the clouds, beyond the realm of mortals, to the eternal halls of Olympus itself. There, Zeus granted Ganymede immortality and appointed him as the cupbearer to the gods, a position of tremendous honour. Forever young, forever beautiful, Ganymede would spend eternity serving nectar and ambrosia to the divine beings who shaped the fate of the universe. This myth resonated deeply with ancient Greek culture and spread throughout the Mediterranean world. The story appeared in countless works of art, from painted pottery to magnificent sculptures. The great poet Homer referenced Ganymede in the Iliad, describing him as the loveliest born of the race of mortals. Philosophers and writers return to this tale again and again, finding in it themes of divine favour, the transcendence of mortality, and the power of beauty to move even the most powerful beings in existence. The Romans adopted this myth, as they did so many Greek stories, though they called the young cupbearer Catamatus in their own tongue. The constellation Aquarius, the water-bearer, became associated with Ganymede in astronomical traditions, forever linking the mythological figure to the night sky. Artists throughout the Renaissance period found inspiration in this ancient tale. Michelangelo created a famous drawing depicting the moment of abduction, showing the eagle carrying the youth heavenward. Rubens, Rembrandt, and countless other masters rendered their own interpretations of this powerful mythological moment. When astronomers of the 17th century began discovering new worlds orbiting distant planets, they turned naturally to classical mythology for names. The tradition of naming celestial bodies after gods, heroes, and mythological figures stretched back to antiquity, when the visible planets received the names of Roman deities. Mercury, Venus, Mars, Jupiter, and Saturn had carried these divine names for thousands of years. It seemed only fitting that the moons of these planets should bear names drawn from the same rich tradition of classical storytelling. Simon Marius, a German astronomer who observed Jupiter's moons around the same time as Galileo, proposed naming the 4 large satellites after figures associated with Jupiter in mythology. Jupiter was the Roman name for Zeus, and so Marius suggested naming the moons after individuals whom Zeus had loved or favoured in the ancient stories. The innermost large moon became Io, named for a priestess whom Zeus transformed into a heifer to hide her from his jealous wife, Hera. The second moon received the name Europa, after the Phoenician princess whom Zeus, again in the form of a bull, carried across the sea to Crete. The third moon, the largest of them all, became Ganymede, the beautiful cupbearer. The outermost of the 4 great moons took the name Callisto, after a nymph whom Zeus loved and whom Hera transformed into a bear. These names did not gain immediate acceptance. For many years, astronomers simply referred to the moons by numbers or by various designation systems. Galileo himself had proposed naming them the Medicean stars, in honour of his patrons, the Medici family of Florence. But over time, the mythological names proposed by Marius gradually won favour. By the 20th century, these names had become standard, and today we cannot imagine calling these worlds by any other designations. Ganymede the moon had inherited the legacy of Ganymede the prince, carrying the ancient name into the space age. The choice of this particular name seems almost prophetic when we consider what we now know about this remarkable moon. Just as the mythological Ganymede was elevated from the mortal realm to dwell among the gods, so too does Ganymede the moon stand elevated above its peers. It is the largest moon in our entire solar system, a world so substantial that it exceeds the planet Mercury in size. If Ganymede orbited the Sun directly rather than circling Jupiter, we would classify it as a planet in its own right. In a sense, this moon has achieved a kind of celestial transcendence, rising above the typical status of a satellite, to become something grander, something more significant. The mythological resonance extends further still. Ganymede the cupbearer served drinks to the gods, and Ganymede the moon harbours a vast ocean of liquid water beneath its icy surface. This hidden sea contains more water than all the oceans of Earth combined, a cosmic reservoir of the substance most essential to life as we understand it. The cupbearer of the gods has become, in astronomical reality, a bearer of water on a scale almost beyond human comprehension. Throughout human history, Ganymede has occupied a special place in our collective imagination about the cosmos. When science fiction writers of the early 20th century began crafting stories set on other worlds, Ganymede frequently appeared as a destination for intrepid space travellers. Authors imagined this distant moon as a frontier for human expansion, a place where colonies might one day take root among the ice and rock. Robert Heinlein set his novel Farmer in the Sky on Ganymede, depicting a future where humans terraform this frozen world into agricultural land. Isaac Asimov, Arthur C. Clarke, and many other luminaries of the genre included Ganymede in their visions of humanity's spacefaring future. These fictional portrayals shaped public perception of Ganymede for generations. The moon became synonymous with the promise of space exploration, a symbol of the vast territories waiting to be discovered beyond Earth. Even as scientific understanding of Ganymede evolved, revealing a world far more hostile to human life than early writers had imagined, the sense of wonder and possibility remained. Ganymede continues to represent the frontier, the unknown, the realm of discovery that calls to the human spirit. In art and popular culture, Ganymede has inspired countless creative works. Musicians have composed pieces evoking the mystery of this distant world. Visual artists have rendered imaginary landscapes of grooved terrain and ancient craters beneath Jupiter's looming presence. Video games have transported players to virtual recreations of Ganymede's surface, allowing them to explore ice fields and peer into shadowed chasms. The moon has become a cultural touchstone, a reference point for discussions of space exploration, astrobiology, and the search for life beyond Earth. The scientific community holds Ganymede in equally high regard. Among planetary scientists, this moon represents one of the most fascinating objects in our solar system, a world that challenges our understanding of how moons form and evolve. The discovery of Ganymede's subsurface ocean transformed our conception of where life might exist in the universe. No longer could we assume that habitable environments required proximity to a star. Ganymede demonstrated that liquid water could persist in the frozen outer reaches of a planetary system, heated not by sunlight but by the gravitational interactions between massive bodies. This revelation expanded the potential territory for life in the cosmos enormously. If a moon orbiting Jupiter could maintain a liquid ocean beneath its surface, similar environments might exist around countless other giant planets throughout the galaxy. The implications for astrobiology were profound and continue to drive scientific research and mission planning to this day. Ganymede stands at the centre of one of the most exciting frontiers in modern science, the search for habitable worlds beyond our own. As we prepare to journey through the complete story of this remarkable moon, from its discovery to the latest scientific findings, from its formation billions of years ago to the missions that will explore it in the years ahead, we carry with us this rich legacy of myth and imagination. Ganymede is not merely a ball of ice and rock orbiting a distant planet. It is a world that has inspired human creativity for centuries, a place that embodies our deepest hopes and curiosities about the universe we inhabit. The story of Ganymede is, in many ways, the story of human wonder itself, our endless desire to understand the cosmos and our place within it. So let us begin this journey together, travelling across the vast gulf of space to a moon that has captivated humanity since the first moment we glimpsed it through a telescope. Let the gentle rhythm of this narrative carry you through the wonders of Ganymede, from ancient myth to cutting-edge science, from the first telescopic observations to the robotic explorers that will soon orbit this frozen world. Close your eyes if you wish, and let your imagination transport you to the outer solar system, where Ganymede waits in the darkness, keeping its secrets beneath a shell of ancient ice. Section 2, The Discovery, Galileo's revolutionary moment. The year was 1609, and the world stood on the brink of a transformation that would reshape human understanding of the cosmos forever. In the Italian city of Padua, a professor of mathematics named Galileo Galilei had heard rumours of a remarkable invention from the Netherlands. Dutch spectacle makers had discovered that arranging lenses in a particular configuration could make distant objects appear closer, as if by magic. This device, which would come to be called the telescope, had initially been conceived as a tool for military and naval purposes, allowing commanders to spot enemy ships or armies from great distances. Galileo recognized immediately that this invention held far greater potential than its creators had imagined. If a telescope could bring distant ships into clear view, what might it reveal about the celestial bodies that wandered through the night sky? The planets, those mysterious lights that moved against the fixed background of stars, had puzzled astronomers since ancient times. Perhaps this new instrument could unveil their true nature. With characteristic energy and brilliance, Galileo set about constructing his own telescopes. He did not merely copy the Dutch design, but improved upon it dramatically, grinding his own lenses with meticulous care to achieve ever greater magnification and clarity. By the autumn of 1609, Galileo had created a telescope that magnified objects approximately 20 times, far surpassing anything the Dutch inventors had achieved. He turned this instrument toward the heavens and began a campaign of observation that would change history. The moon was among his first targets, and what he saw astonished him. The lunar surface was not the smooth, perfect sphere that ancient philosophers had imagined, but a rugged landscape of mountains, valleys, and circular formations we now call craters. The boundary between light and shadow on the moon's surface revealed topography as dramatic as any on Earth. This observation alone challenged centuries of astronomical doctrine, which held that celestial bodies were fundamentally different from earthly matter, composed of perfect, unchanging substance. But Galileo's most revolutionary discoveries awaited him when he turned his telescope toward Jupiter. On the night of January 7th, 1610, he observed the giant planet and noticed 3 small stars arranged in a line near it, 2 to the east and 1 to the west. Galileo recorded their positions carefully, assuming they were simply background stars that happened to lie along Jupiter's path through the sky. The following night, January 8th, Galileo looked again and found something puzzling. The 3 small stars were still there, but their arrangement had changed. Now all 3 appeared to the west of Jupiter. Had the planet moved eastward past them? This seemed inconsistent with Jupiter's known motion through the zodiac. Galileo's curiosity was aroused, and he resolved to continue his observations. Clouds obscured the sky on January 9th, preventing observation. But on January 10th, Galileo found only 2 of the small stars visible, both to the east of Jupiter. One seemed to have vanished entirely. On subsequent nights, the configuration continued to change in ways that could not be explained by Jupiter's motion against the background stars. Sometimes 3 stars were visible, sometimes 4. They shifted positions from night to night, appearing first on one side of the planet, then the other. As Galileo accumulated observations over the following weeks, the truth gradually became clear to him. These were not stars at all. They were moons, satellites orbiting Jupiter just as our own moon orbits Earth. Their changing positions reflected their orbital motion around the giant planet. When a moon passed behind Jupiter, it disappeared from view, explaining the occasional apparent vanishing of one of the objects. This realization struck at the very foundations of the astronomical worldview that had dominated Western thought for nearly 2,000 years. The geocentric model, which placed Earth at the center of the universe, with all celestial bodies revolving around it, had no place for moons orbiting other planets. If Jupiter could have satellites circling it, while Jupiter itself moved through space, then Earth's status as the unique center of cosmic motion was called into question. The Copernican hypothesis, which placed the Sun at the center of the planetary system, suddenly seemed far more plausible. Galileo understood the significance of his discovery and moved quickly to announce it to the world. In March 1610, he published a small book titled Sidereus Nuncius, which translates as Starry Messenger, or sometimes as Starry Message. In this remarkable document, Galileo described his telescopic observations of the Moon, the stars, and most importantly, the moons of Jupiter. He included diagrams showing the changing positions of the satellites on different nights, providing evidence that any reader with a telescope could verify for themselves. The publication of Sidereus Nuncius created a sensation throughout Europe. Copies of the book spread rapidly, and astronomers everywhere scrambled to obtain telescopes so they could see these wonders for themselves. Some initially doubted Galileo's claims, suspecting that the apparent moons might be optical artifacts produced by the telescope itself. But as more observers confirmed the existence of Jupiter's satellites, skepticism gave way to amazement. Galileo had discovered 4 moons orbiting Jupiter, and these 4 remain the largest and most significant of the giant planet's many satellites. They would eventually be named Io, Europa, Ganymede, and Callisto, though Galileo himself called them the Medicean stars in honour of Cosimo de' Medici, the Grand Duke of Tuscany. Galileo hoped that this dedication would secure him patronage and protection, and indeed Cosimo appointed him as his official philosopher and mathematician shortly after the publication of Sidereus Nuncius. Among the 4 moons, Ganymede was the largest, though Galileo could not have known this from his observations. Through his telescope, the moons appeared merely as points of light, their disks too small to resolve. He could track their motions and estimate their orbital periods, but details of their surfaces, sizes, and compositions remained hidden. Centuries would pass before humanity gained a clearer picture of these distant worlds. The naming of Jupiter's moons involved a curious historical episode that deserves attention. While Galileo's observations are universally credited as the first, a German astronomer named Simon Marius claimed to have observed the moons independently, possibly even before Galileo. Marius published his own account in 1649, 4 years after Siderius Nuncius, which naturally raised suspicions that he had simply borrowed Galileo's discovery. The dispute over priority became bitter, with Galileo accusing Marius of plagiarism. Modern historians have examined the evidence and concluded that Marius likely did observe Jupiter's moons independently, though probably a few days after Galileo's first observations. The delay in publication appears to have resulted from Marius's more cautious approach rather than any attempt at deception. Regardless of the priority dispute, it was Marius who proposed the mythological names that we use today. In his 1614 publication, Marius suggested naming the moons after figures associated with Jupiter in classical mythology, and these names gradually gained acceptance over the following centuries. Ganymede, as the third moon from Jupiter, occupies a middle position among the Galilean satellites. It orbits beyond Io and Europa, but closer than Callisto. Galileo observed that it completed one orbit around Jupiter in approximately 7 Earth days, a figure remarkably close to the modern value of 7.15 days. This orbital period meant that Ganymede's position changed noticeably from night to night, making it relatively easy to track against the background of stars. The discovery of Jupiter's moons had implications that extended far beyond astronomy. It provided powerful support for the Copernican model of the solar system, in which Earth was merely one of several planets orbiting the Sun. If moons could orbit Jupiter while Jupiter moved through space, then Earth's moon could orbit Earth while Earth moved around the Sun. The philosophical objection that Earth could not be in motion because its moon would be left behind was effectively refuted. Furthermore, the discovery demonstrated that the universe was far more complex and interesting than ancient authorities had supposed. Aristotle and Ptolemy, whose writings had dominated astronomical thought for centuries, had known nothing of these moons. Their absence from ancient texts proved that observation and investigation could reveal truths that pure reason and philosophical speculation could never uncover. The scientific method, with its emphasis on empirical evidence and systematic observation, gained credibility at the expense of received wisdom and traditional authority. For Galileo personally, the discovery of Jupiter's moons marked the beginning of a tumultuous period that would see him celebrated as one of the greatest scientists of his age and condemned as a heretic by the Catholic Church. His advocacy for the Copernican system eventually brought him into conflict with religious authorities, leading to his famous trial and house arrest in the final years of his life. But the truth of his discoveries could not be suppressed. The moons of Jupiter continue to orbit their parent planet, visible to anyone with a telescope, silent witnesses to the power of observation over dogma. In the centuries following Galileo's discovery, astronomers continued to study Jupiter's moons with ever more sophisticated instruments. Telescopes grew larger and more powerful, revealing additional details about these distant worlds. Observers measured the moon's orbital periods with increasing precision and began to estimate their sizes based on their brightness. Ganymede, as the largest and brightest of the four, attracted particular attention. The development of spectroscopy in the 19th century allowed astronomers to begin analysing the composition of celestial bodies by studying the light they reflected or emitted. Early spectroscopic observations of Ganymede suggested the presence of water ice on its surface, a finding that would be confirmed and elaborated by later studies. The moon's relatively high reflectivity, or albedo, was consistent with an icy surface, distinguishing it from the rocky inner planets and asteroids. As the 20th century progressed, ground-based observations of Ganymede became increasingly sophisticated. Astronomers mapped variations in surface brightness, identifying regions of different reflectivity that hinted at geological diversity. They measured the moon's size more accurately, confirming that it exceeded Mercury in diameter. They studied the thermal radiation emitted by Ganymede's surface, gaining information about surface temperatures and thermal properties. Yet for all these advances, Ganymede remained fundamentally mysterious. The moon was simply too far away and too small in apparent size for Earth-based telescopes to reveal surface features in detail. The grooves, craters, and varied terrains that we now know characterize Ganymede's surface were invisible to even the most powerful ground-based instruments. To truly understand this moon, humanity would need to send spacecraft across the vast gulf of space to observe it up close. The space age, which began with the launch of Sputnik in 1957, eventually made such missions possible. In the 1970s, NASA launched Pioneer 10 and Pioneer 11, the first spacecraft to venture into the outer solar system. These hardy probes flew past Jupiter, returning the first close-up images of the giant planet and its moons. Though the Pioneer images were crude by later standards, they revealed that Ganymede was a world of varied terrain, with both dark and light regions visible on its surface. The Voyager missions of the late 1970s and early 1980s provided far more detailed views. Voyager 1 and Voyager 2 flew through the Jupiter system, capturing images that transformed our understanding of the Galilean moons. Ganymede emerged as a complex world with two distinct types of terrain: ancient, dark, heavily cratered regions and younger, brighter areas marked by intricate patterns of grooves and ridges. The moon's surface told a story of geological activity extending over billions of years, a history written in ice and rock. The Galileo spacecraft, which arrived at Jupiter in 1995 and spent 8 years studying the planet and its moons, provided the most detailed examination of Ganymede to date. Named in honour of the astronomer who first glimpsed these moons nearly 4 centuries earlier, the Galileo mission made multiple close flybys of Ganymede, returning images with resolution measured in meters rather than kilometers. These observations revealed the moon's surface in unprecedented detail, showing individual craters, grooves, and geological formations. Perhaps most remarkably, the Galileo mission discovered that Ganymede possesses its own magnetic field, making it the only moon in the solar system known to have one. This finding had profound implications for understanding Ganymede's interior structure and suggested the presence of a liquid layer beneath the surface, possibly a vast ocean of water. The cupbearer of the gods, it seemed, truly did bear water in abundance. From Galileo's first glimpse through a crude telescope to the sophisticated observations of modern spacecraft, our understanding of Ganymede has grown enormously. Yet in another sense, we have only begun to explore this remarkable world. The questions that remain unanswered far outnumber those we have resolved. What lies beneath Ganymede's icy surface? Could life exist in its hidden ocean? What can this moon teach us about the formation and evolution of planetary systems? These questions drive ongoing scientific research and will motivate future missions to the Jupiter system. As we continue our journey through the story of Ganymede, we carry with us the spirit of discovery that animated Galileo on those cold January nights in 1610. The same curiosity that drove him to point his telescope at Jupiter drives scientists today to send spacecraft across billions of kilometres of space. The same wonder that filled him when he realised he was seeing moons orbiting another planet fills us when we contemplate the possibility of alien oceans and the potential for life beyond Earth. Ganymede connects us to our past and beckons us toward our future, a world that has inspired humanity for 4 centuries and will continue to do so for centuries to come. Section 3. Jupiter's family. Context of the Galilean moons. To truly understand Ganymede, we must first appreciate the remarkable family of worlds to which it belongs. Jupiter, the giant planet that Ganymede calls home, presides over a vast system of moons that resembles a miniature solar system in its own right. More than 95 moons orbit this colossal world, ranging from tiny irregular fragments barely a kilometre across to enormous spherical bodies that would qualify as planets if they orbited the Sun directly. Among this diverse collection, 4 moons stand apart in size and significance. These are the Galilean moons, named for their discoverer, and they represent some of the most fascinating worlds in our cosmic neighbourhood. Jupiter itself is a world of staggering proportions. This gas giant contains more mass than all the other planets in our solar system combined, wrapped into a sphere so vast that more than 1,300 Earths could fit inside it. Bands of ammonia clouds encircle the planet in shades of cream, orange and brown, driven by winds that howl at hundreds of kilometres per hour. The Great Red Spot, a storm larger than Earth itself, has raged in Jupiter's atmosphere for centuries, a testament to the tremendous energy churning within this massive world. The planet's immense gravity reaches far into surrounding space, capturing and holding objects that venture too close. Over the billions of years since Jupiter formed, it has accumulated a retinue of satellites that orbit at various distances, from moons that skim just above the cloud tops to distant, irregular satellites that take years to complete a single orbit. The 4 Galilean moons occupy a special zone relatively close to Jupiter, where conditions allowed large spherical bodies to form and persist. Io, the innermost of the Galilean moons, orbits Jupiter at a distance of approximately 422,000 kilometres, completing one circuit around the planet in just 1.77 Earth days. This proximity to Jupiter has dramatic consequences for Io's character. The giant planet's gravitational pull, combined with the gravitational influences of the other Galilean moons, subjects Io to tremendous tidal forces. As Io moves through its slightly elliptical orbit, these tidal forces flex and squeeze the moon's interior, generating enormous amounts of heat through friction. This tidal heating has transformed Io into the most volcanically active body in the known solar system. Hundreds of volcanoes dot its surface, some of which erupt continuously, sending plumes of sulfur and sulfur dioxide hundreds of kilometres into space. The moon's surface is painted in vivid yellows, oranges, reds and blacks, a palette created by various sulfur compounds deposited by volcanic activity. No impact craters survive on Io's surface because volcanic eruptions constantly resurface the moon, burying any craters beneath fresh layers of lava and volcanic debris. The landscape of Io presents a vision of geological violence almost beyond imagination. Mountains tower above the sulphurous plains, some reaching heights of 17 kilometres, taller than any mountain on Earth. These peaks are not volcanic cones, but rather tectonic structures, thrust upward by the tremendous forces acting on Io's crust. Lava lakes glow with molten rock, their surfaces crusting over and breaking apart in endless cycles. Volcanic vents release gases that freeze almost instantly in the cold vacuum of space, creating delicate frosts of sulfur dioxide that coat the surrounding terrain. Despite its hellish conditions, Io plays a crucial role in the Jupiter system. The volcanic gases it releases escape into space and become ionized by solar radiation and Jupiter's intense magnetic field. These ions form a donut-shaped ring around Jupiter called the Io plasma torus, a region of charged particles that interacts with Jupiter's magnetosphere in complex ways. Io essentially feeds material into the Jovian environment, influencing conditions throughout the inner reaches of Jupiter's domain. Europa, the second Galilean moon, orbits at approximately 671,000 kilometers from Jupiter, completing one orbit every 3.55 Earth days. Slightly smaller than Earth's moon, Europa presents a dramatically different appearance from its volcanic neighbour. The surface of Europa is covered almost entirely by water ice, creating a world of brilliant white and subtle brown streaks that crisscross the frozen landscape. This icy shell is remarkably smooth on a global scale, with very few large impact craters marring its surface. The scarcity of craters on Europa tells scientists something profound about this moon. Impact craters accumulate over time as asteroids and comets strike a world's surface. A surface with few craters must be geologically young, constantly renewed by processes that erase the scars of ancient impacts. On Europa, this renewal appears to come from below. The ice shell is not static but dynamic, cracked and shifted by forces originating in the moon's interior. Beneath Europa's frozen exterior lies what may be the most tantalizing ocean in our solar system. Scientists believe that a global sea of liquid water exists beneath the ice, kept liquid by tidal heating similar to, but less intense than the heating that drives Io's volcanism. This ocean may contain twice as much water as all of Earth's oceans combined, hidden beneath an ice shell estimated to be between 15 and 25 kilometers thick. The surface of Europa bears witness to the ocean below. Long linear features called linea stretch for thousands of kilometers across the ice, marking places where the shell has cracked and shifted. Regions of chaotic terrain show where the ice has broken into jumbled blocks, perhaps where warmer water welled up from below. Reddish-brown material stains the ice in many locations, possibly salts or organic compounds that have risen from the ocean through cracks in the shell. Europa has become a prime target in the search for life beyond Earth. The combination of liquid water, chemical energy from interactions between water and rock, and the organic compounds that comets and asteroids may have delivered creates conditions potentially suitable for life. Some scientists speculate that hydrothermal vents on Europa's ocean floor, similar to those that support thriving ecosystems in Earth's deep oceans, might harbour alien organisms. Future missions aim to investigate this possibility, seeking signs of life in one of the most promising locations in our solar system. Beyond Europa's orbit, we find Ganymede, the subject of our extended journey tonight. Orbiting at approximately 1,070,000 kilometers from Jupiter, Ganymede takes 7.15 Earth days to complete one trip around the giant planet. This greater distance from Jupiter means that Ganymede experiences less intense tidal heating than Io or Europa, resulting in a world that is geologically less active but no less fascinating. Ganymede stands apart from its siblings in several important ways. It is the largest moon in the entire solar system, exceeding even Saturn's giant moon Titan in size. Its diameter of 5,268 kilometers makes it larger than the planet Mercury, though its lower density means it contains less mass than that small rocky world. If Ganymede orbited the Sun rather than Jupiter, we would almost certainly classify it as a planet. The surface of Ganymede displays two distinct types of terrain that tell different chapters of the Moon's geological history. Dark regions, covering about 1/3 of the surface, represent ancient crust that has accumulated impact craters over billions of years. These areas, with names like Galileo Regio and Marius Regio, preserve a record of the intense bombardment that characterized the early solar system. Bright regions, making up the remaining 2/3 of the surface, are younger and marked by intricate patterns of grooves and ridges that speak of geological activity in Ganymede's past. Unlike Io, Ganymede is not currently volcanically active. Unlike Europa, its surface is not being constantly renewed by processes from below. Yet Ganymede possesses something that neither of its inner siblings has: its own internally generated magnetic field. This magnetic field, discovered by the Galileo spacecraft in 1996, makes Ganymede unique among all the moons in our solar system. The existence of this field suggests that Ganymede's interior contains a layer of electrically conducting fluid, most likely a convecting iron core similar to the one that generates Earth's magnetic field. Ganymede also harbours a subsurface ocean, though this ocean lies deeper beneath the surface than Europa's and is sandwiched between layers of ice. The structure of Ganymede's interior is complex, with an iron core at the centre, surrounded by a rocky mantle, topped by layers of ice in various phases, with the liquid ocean residing between ice layers. This configuration makes Ganymede a world of hidden depths, its secrets buried beneath hundreds of kilometres of frozen material. Callisto, the outermost of the Galilean moons, orbits at approximately 183,000 kilometres from Jupiter, taking 16.69 Earth days to complete one orbit. This great distance places Callisto outside the orbital resonance that links Io, Europa, and Ganymede, resulting in a world that has experienced minimal tidal heating throughout its history. Callisto is the most heavily cratered object in the solar system, its ancient surface preserving a record of impacts stretching back billions of years. The appearance of Callisto could hardly be more different from that of Io. Where Io blazes with volcanic colours, Callisto presents a uniformly dark, battered face to the cosmos. Impact craters of all sizes cover virtually every square kilometre of its surface, from tiny pits to enormous multi-ring basins hundreds of kilometres across. The largest of these impact structures, Valhalla, spans approximately 3,800 kilometres when its outermost rings are included, making it one of the largest impact features in the solar system. Despite its apparently dead surface, Callisto may also possess a subsurface ocean. Measurements of how Callisto responds to Jupiter's varying magnetic field suggest the presence of an electrically conducting layer beneath the surface, most likely salty liquid water. If this ocean exists, it lies very deep beneath Callisto's icy crust, perhaps 200 kilometres or more below the surface. The existence of an ocean on such a geologically inactive world would demonstrate that liquid water can persist in surprising locations throughout the outer solar system. The 4 Galilean moons exist in a remarkable gravitational relationship known as orbital resonance. For every orbit that Ganymede completes around Jupiter, Europa completes exactly 2 orbits, and Io completes exactly 4. This precise mathematical relationship is not coincidental, but results from gravitational interactions between the moons over billions of years. The resonance locks the moons into their current orbital configuration and ensures that they regularly align in specific patterns. This orbital resonance has profound consequences for the inner 3 moons. The regular gravitational tugs that Io, Europa, and Ganymede exert on each other prevent their orbits from becoming perfectly circular. The slight ellipticity of their orbits means that their distance from Jupiter varies as they travel around the planet. This variation in distance causes the tidal forces acting on each moon to fluctuate, flexing their interiors and generating heat. Without the orbital resonance, the orbits would have circularized long ago, and the tidal heating that drives Io's volcanism and maintains Europa's ocean would have ceased. Ganymede's position in this resonance means it experiences some tidal heating, though far less than Io or Europa. This modest heat input may have contributed to geological activity in Ganymede's past and may help maintain the liquid ocean that scientists believe exists beneath its surface. The resonance thus connects the fates of the three inner Galilean moons, linking their orbital dynamics to their internal structures and geological histories. Callisto, orbiting beyond the resonance, has followed a different evolutionary path. Without significant tidal heating, Callisto's interior has remained relatively cold throughout its history. The moon never fully differentiated into distinct layers of rock and ice, the way Ganymede did. Instead, Callisto's interior appears to be a relatively uniform mixture of rock and ice, only partially separated into layers. This incomplete differentiation makes Callisto a valuable point of comparison for understanding how moons evolve under different conditions. The contrast between Ganymede and Callisto is particularly instructive. These two moons are similar in size and overall composition, yet they have evolved very differently. Ganymede is fully differentiated, with a distinct iron core, rocky mantle, and ice shell. It possesses a magnetic field and shows evidence of past geological activity. Callisto, by contrast, is only partially differentiated, lacks a magnetic field, and shows no signs of geological activity beyond impact cratering. The key difference appears to be tidal heating. Ganymede's participation in the orbital resonance provided enough internal heat to drive differentiation and geological processes, while Callisto remained cold and geologically stagnant. Together, the four Galilean moons represent a spectrum of geological possibilities for icy worlds. Io demonstrates the extreme effects of intense tidal heating, with continuous volcanic activity erasing all traces of impact history. Europa shows moderate tidal heating maintaining a subsurface ocean and driving ongoing geological renewal of the surface. Ganymede displays the legacy of past geological activity combined with a complex layered interior. Callisto preserves an ancient surface that records billions of years of impact history with minimal modification. This diversity makes the Jupiter system an invaluable natural laboratory for studying planetary processes. By comparing the four Galilean moons, scientists can understand how factors like distance from a parent planet, tidal heating, and orbital dynamics influence the evolution of worlds. The insights gained from studying these moons extend far beyond the Jupiter system, informing our understanding of icy moons throughout the solar system and around other stars. As we focus our attention on Ganymede in the sections ahead, we should keep in mind its place within this remarkable family of worlds. Ganymede does not exist in isolation, but as part of a dynamic system shaped by gravitational interactions, tidal forces, and billions of years of coevolution. Understanding Ganymede means understanding its relationship to Jupiter and its sibling moons, appreciating how this largest of all satellites came to be the world we observe today. Section 4. Ganymede's Vital Statistics, a world of superlatives. Numbers alone cannot capture the wonder of a world like Ganymede, yet they provide a foundation for understanding just how remarkable this moon truly is. When we examine the vital statistics of Ganymede, we encounter a litany of superlatives, records, and comparisons that set this moon apart from every other satellite in our solar system. Let us explore these measurements in detail, translating cold figures into vivid understanding of what kind of world Ganymede represents. The diameter of Ganymede measures 5,268 kilometers from one side to the other. To appreciate this figure, consider that Mercury, the innermost planet of our solar system, has a diameter of only 4,879 kilometers. Ganymede exceeds Mercury's size by nearly 400 kilometers, making it the only moon in the solar system larger than a planet. If you could somehow place Ganymede and Mercury side by side, the moon would noticeably dwarf the planet, a remarkable reversal of our usual expectations about the relative sizes of planets and their satellites. The comparison with Mercury illuminates Ganymede's planetary nature, but other comparisons help us grasp its scale in more familiar terms. Earth's moon, the celestial body that has accompanied our planet throughout human history, measures 3,475 kilometers in diameter. Ganymede is more than 50% larger, so much bigger that if our moon were replaced by Ganymede, the night sky would be dominated by a dramatically larger orb. Mars, the red planet that has captured human imagination for centuries, has a diameter of 6,179 kilometers. Ganymede reaches about 3/4 of this size, making it comparable to one of the most studied planets in our solar system. The surface area of Ganymede encompasses approximately 87 million square kilometers. This vast expanse exceeds the combined land area of all the continents on Earth, which totals roughly 150 million square kilometers when oceans are excluded. Imagine every forest, desert, mountain range, and plain on our planet gathered together, and Ganymede's surface would still extend beyond them. This enormous area contains countless geological features waiting to be explored, from ancient cratered plains to intricate grooved terrain, from towering scarps to subtle colour variations that hint at compositional differences. Despite its impressive size, Ganymede contains considerably less mass than its dimensions might suggest. The Moon's mass measures approximately 1.48 times 10 to the 23rd kilograms, which amounts to about 2.02 times the mass of Earth's moon. Mercury, though smaller in diameter, actually contains more mass than Ganymede because Mercury is composed primarily of dense rock and iron, while Ganymede consists of a mixture of rock and water ice. This difference in composition fundamentally shapes the character of each world. The density of Ganymede, calculated by dividing its mass by its volume, comes to approximately 1.94 grams per cubic centimetre. For comparison, Earth's average density is about 5.5 grams per cubic centimetre, while pure water has a density of exactly 1 gram per cubic centimetre. Ganymede's intermediate density tells us that the Moon contains a substantial fraction of water ice mixed with denser rocky material. Scientists estimate that Ganymede is composed of roughly equal parts rock and ice by mass, with the proportions varying at different depths within the Moon's interior. The surface gravity on Ganymede measures approximately 1.43 meters per second squared, which translates to about 0.146 times Earth's surface gravity. If you could stand on Ganymede's surface, you would weigh only about 1/7 of your Earth weight. A person who weighs 70 kilograms on Earth would weigh only about 10 kilograms on Ganymede. This low gravity would make movement feel strange and dreamlike, with each step carrying you higher and farther than you might expect. Jumping would send you soaring to heights impossible on Earth, and objects would fall with an almost lazy slowness. This reduced gravity has important implications for Ganymede's ability to retain an atmosphere. A world's gravity determines how easily gas molecules can escape into space. On Ganymede, the relatively weak gravitational pull means that light gas molecules like hydrogen and helium escape readily, while heavier molecules can persist for longer periods. The Moon does possess an extremely thin atmosphere, but it is far too tenuous to be breathable or to significantly affect surface conditions. Ganymede orbits Jupiter at an average distance of approximately 1,070,400 kilometers, measured from the center of Jupiter to the center of Ganymede. This distance places Ganymede well beyond the orbits of Io and Europa, but closer than Callisto. To put this orbital distance in perspective, Earth's moon orbits our planet at an average distance of of about 384,400 kilometres. Ganymede orbits nearly 3 times farther from Jupiter than our moon orbits from Earth. Yet Jupiter's immense size means that the giant planet still dominates Ganymede's sky. The orbital period of Ganymede, the time required for the moon to complete one circuit around Jupiter, measures approximately 7.15 Earth days. This period places Ganymede in a precise orbital resonance with Io and Europa, as we discussed earlier. For every orbit Ganymede completes, Europa completes exactly 2 orbits, and Io completes exactly 4. This mathematical relationship has persisted for billions of years, and will continue far into the future, locking the 3 moons into a gravitational dance around their parent planet. Ganymede's orbit is nearly circular, with an eccentricity of only about 3. This means that the moon's distance from Jupiter varies by less than 1% over the course of an orbit. The near circularity of the orbit results from the tidal interactions with Jupiter over billions of years, which have gradually removed energy from any initial orbital elongation. However, the orbital resonance with Io and Europa prevents the orbit from becoming perfectly circular, maintaining a small but significant eccentricity that contributes to tidal heating within Ganymede's interior. The orbital inclination of Ganymede, the angle between its orbital plane and Jupiter's equatorial plane, measures only about 0.2 degrees. This nearly equatorial orbit means that Ganymede travels around Jupiter in almost the same plane as the planet's equator, a configuration typical of large moons that formed from the same disk of material as their parent planet. The low inclination also means that Ganymede regularly passes through Jupiter's shadow, experiencing eclipses that plunge the moon into darkness. Like most large moons in the solar system, Ganymede is tidally locked to Jupiter, meaning that the same hemisphere always faces the giant planet. This synchronous rotation results from tidal forces that have gradually slowed Ganymede's rotation over billions of years until the rotational period exactly matches the orbital period. A day on Ganymede, measured from one noon to the next at a fixed location, lasts the same 7 or 15 Earth days as the moon's orbital period. The tidal locking creates 2 distinct hemispheres on Ganymede: the subjovian hemisphere, which always faces Jupiter, and the antijovian hemisphere, which always faces away. From the subjovian hemisphere, Jupiter would hang motionless in the sky, a massive presence that never rises or sets but slowly changes phase as Ganymede orbits around it. From the antijovian hemisphere, Jupiter would never be visible at all, hidden forever beyond the horizon. The leading hemisphere, which faces forward in the direction of orbital motion, and the trailing hemisphere, which faces backward, experience different rates of bombardment by micrometeoroids and charged particles, leading to subtle differences in surface properties. The temperatures on Ganymede's surface vary depending on location and time of day, but they are universally frigid by earthly standards. Daytime temperatures at the equator can reach approximately 110 Kelvin, which corresponds to negative 163 degrees Celsius or negative 261 degrees Fahrenheit. Nighttime temperatures plunge even lower, dropping to around 70 Kelvin or negative 203 degrees Celsius, negative 333 degrees Fahrenheit. At the poles, where sunlight strikes at low angles and provides minimal heating, temperatures remain near the nighttime values, even during the day. These extreme cold temperatures ensure that water ice, which makes up much of Ganymede's surface, remains as hard as rock. On Earth, we think of ice as a relatively fragile material that melts easily and flows under pressure. On Ganymede, ice at these temperatures behaves more like stone, maintaining its shape over geological timescales and fracturing under stress rather than flowing. The grooves and ridges that mark Ganymede's bright terrain formed through tectonic processes acting on this rigid ice shell, cracking and shifting the surface much as plate tectonics shapes Earth's rocky crust. The escape velocity from Ganymede's surface, the speed required for an object to break free of the Moon's gravity entirely, measures approximately 2.74 kilometers per second. This figure is low compared to Earth's escape velocity of 11.2 kilometers per second, but high enough that Ganymede has retained heavier atmospheric molecules over geological time. The escape velocity also determines how difficult it would be to launch spacecraft from Ganymede's surface, an important consideration for any future human presence on this moon. Ganymede receives sunlight at an intensity of approximately 50 watts per square metre, compared to about 1,361 watts per square metre at Earth's distance from the Sun. This dramatic reduction in solar energy results from Jupiter's great distance from the Sun, approximately 5.2 times farther than Earth's orbit. The dim sunlight provides minimal heating and would appear noticeably fainter to human eyes, though still bright enough to see clearly. The Sun itself would appear as a small but intensely bright point, about 1/5 the diameter it appears from Earth, but still too brilliant to look at directly. The journey from Earth to Ganymede spans an immense distance that varies as both planets move in their orbits. At its closest approach, when Earth and Jupiter are on the same side of the Sun, the distance measures approximately 628 million kilometers. At its farthest, when the two planets are on opposite sides of the Sun, the distance stretches to about 928 million kilometers. Even at the speed of light, signals take between 35 and 52 minutes to travel between Earth and Ganymede, making real-time communication with spacecraft impossible. Commands must be sent in advance, and spacecraft must operate autonomously during critical maneuvers. These vital statistics paint a portrait of a world that defies easy categorization. Ganymede is larger than a planet, yet orbits another world as a moon. It is composed of materials that on Earth we consider soft and transient, yet on Ganymede form a rigid and enduring crust. It experiences conditions so cold that water becomes stone, and so remote that sunlight provides only a feeble glow. Yet within this frozen exterior lies a complex interior with a metallic core, a rocky mantle, layers of ice, and a hidden ocean of liquid water. Understanding these numbers helps us appreciate the challenges facing any attempt to explore Ganymede directly. Spacecraft must travel for years to reach this distant moon, surviving the harsh radiation environment near Jupiter and operating in conditions vastly different from anything on Earth. Yet the same numbers that describe these challenges also describe the rewards of exploration. A world larger than Mercury, with a surface area exceeding Earth's continents, harbouring an ocean that may contain more water than all of Earth's seas combined. As we continue our journey through the story of Ganymede, these statistics will provide context for understanding the Moon's geological features, its internal structure, and its potential for harbouring life. Numbers transform into landscapes, measurements become environments, and statistics reveal a world waiting to be explored. Ganymede's vital statistics are not merely data points, but the vital signs of a living world, a place with its own history, its own processes, and its own mysteries yet to be unravelled. Section 5. Surface Features. Geography of an Alien World. Imagine yourself descending through the darkness of space toward Ganymede, watching as the moon grows from a distant point of light into a vast curved horizon stretching beneath you. As details emerge from the blur of distance, you begin to perceive a world unlike any other, a landscape painted in shades of grey and brown, etched with patterns that speak of billions of years of geological history. The surface of Ganymede tells stories written in ice and rock, narratives of ancient catastrophes and slow transformations that have shaped this moon into the world we observe today. The most striking feature visible from orbit is the dramatic contrast between two fundamentally different types of terrain. Approximately 1/3 of Ganymede's surface consists of dark regions, ancient landscapes that have accumulated the scars of countless impacts over billions of years. The remaining 2/3 of the surface is covered by bright terrain, younger regions marked by intricate patterns of grooves, ridges, and fractures that record episodes of geological activity in Ganymede's past. This division between dark and light creates a patchwork appearance that distinguishes Ganymede from any other world in our solar system. The dark regions of Ganymede represent the oldest surviving surfaces on this moon, windows into the distant past when the solar system was a far more violent place. These ancient terrains are heavily cratered, their surfaces pockmarked by impacts that occurred during the late heavy bombardment, a period approximately 4 billion years ago when the inner solar system was swept by a storm of asteroids and comets. The dark coloration results from a combination of factors, including the accumulation of rocky debris from impacts and the gradual darkening of ice through exposure to radiation and charged particles from Jupiter's magnetosphere. Galileo Regio, named in honor of the astronomer who first glimpsed this moon, stands as the largest of the dark regions on Ganymede. This ancient terrain spans approximately 3,200 kilometers across, an expanse larger than the Mediterranean Sea. The surface of Galileo Regio is saturated with impact craters, meaning that new impacts can only form by destroying older craters, having reached a state of equilibrium where the rate of crater formation equals the rate of crater destruction. Walking across this landscape, if such a journey were possible, would mean traversing an endless succession of circular depressions, crater walls rising and falling like frozen waves on a dark sea. Other significant dark regions include Marius Regio, named for Simon Marius, who independently observed Jupiter's moons, and Perrine Regio, honouring the astronomer Charles Dillon Perrine. Each of these ancient terrains preserves its own record of impacts, its own collection of craters ranging from tiny pits to vast basins. The boundaries between dark regions and the surrounding bright terrain are often sharp and well defined, suggesting that the bright terrain formed through processes that cleanly resurfaced portions of the older dark crust. The bright terrain that covers most of Ganymede's surface presents a dramatically different character. These regions are younger than the dark terrain, though still ancient by earthly standards, with ages estimated between 2 and 4 billion years. The defining characteristic of bright terrain is the presence of grooves, parallel or subparallel furrows that stretch across the surface in complex patterns. These grooves typically measure a few hundred meters to a few kilometers in width and can extend for hundreds of kilometers in length, creating a texture that resembles the surface of a vinyl record magnified to planetary scale. The formation of grooved terrain remains one of the most intriguing puzzles in Ganymede's geological history. Scientists believe that these features formed through tectonic processes, the stretching and fracturing of Ganymede's icy crust in response to stresses from within. As the moon's interior evolved, perhaps through the freezing of subsurface water or the settling of denser materials toward the core, the surface experienced tension that pulled it apart. The crust fractured along parallel lines, creating the grooves we observe today. Different regions of bright terrain display different groove patterns, suggesting multiple episodes of tectonic activity occurring at different times and under different stress conditions. Some areas show grooves running in a single dominant direction, while others display intersecting sets of grooves that record changing stress orientations over time. The complexity of these patterns indicates that Ganymede's geological history was not a simple linear progression, but a series of events, each leaving its own signature on the surface. Uruk Sulcus represents one of the most spectacular examples of grooved terrain on Ganymede. This region, named after the ancient Mesopotamian city, displays exceptionally well-developed groove systems that have been imaged in detail by spacecraft. The grooves of Uruk Sulcus run in sweeping curves across the landscape, their parallel ridges and troughs creating a mesmerizing pattern when viewed from above. High-resolution images reveal that the grooves themselves contain finer-scale features, smaller ridges and fractures that add texture to the larger structures. The bright terrain is not uniformly grooved throughout. Some areas display smooth plains with relatively few grooves, while others are intensely furrowed with closely spaced parallel features. This variation suggests that the processes forming grooved terrain operated with different intensities in different locations, or that some regions have been modified by subsequent events that partially erased the original groove patterns. Understanding this variation remains an active area of research, with scientists working to reconstruct the sequence of events that created Ganymede's diverse landscapes. Impact craters dot both the dark and bright terrains of Ganymede, though their appearance differs between the two surface types. On the dark terrain, craters display the classic bowl-shaped morphology familiar from the Moon and Mercury, with raised rims, depressed floors, and sometimes central peaks formed by the rebound of material after impact. These craters have been preserved for billions of years, their forms modified only slightly by the slow processes of ice relaxation and subsequent smaller impacts. On the bright terrain, craters often appear softer and more subdued, their rims less sharply defined and their floors partially filled with smooth material. This difference reflects the relative youth of the bright terrain and the different properties of the icy surface. Fresh craters on bright terrain may also be partially obscured by the groove patterns, making them harder to identify and study. The interaction between impact cratering and tectonic groove formation provides clues about the timing of different geological events on Ganymede. Among the most fascinating crater-related features on Ganymede are the palimpsests, circular bright spots that represent the ghosts of ancient impact basins. The term palimpsest comes from the practice of scraping and reusing parchment in medieval times, leaving traces of earlier writing beneath newer text. On Ganymede, palimpsests are the traces of large impacts that have been almost completely erased by subsequent geological processes, leaving only subtle circular brightening of the surface to mark where they once existed. The formation of palimpsests likely involves the viscous relaxation of ice over geological timescales. When a large impact excavates a crater in Ganymede's icy crust, the resulting depression represents a gravitational instability. Over millions or billions of years, the ice slowly flows to fill in the depression, much as honey poured into a bowl will eventually level itself. The bright material exposed by the impact remains visible, even after the topographic expression of the crater has been erased, creating the ghostly circular features we observe today. Troe's crater stands as one of the most prominent impact features on Ganymede, a relatively fresh crater approximately 93 kilometers in diameter, located in the dark terrain of Phrygia Sulcus. The crater displays a well-preserved central peak and a system of bright rays extending outward from the impact site. These rays consist of material ejected during the impact, spread across the surrounding surface in a pattern that radiates from the crater like the spokes of a wheel. The brightness of the rays indicates that they exposed fresh ice from beneath the darkened surface layer. Other notable craters include Anat, a 38-kilometer crater with a distinctive dark floor, and Osiris, a 107-kilometre crater that displays complex internal structure, including a central dome. Each crater tells its own story of a violent moment in Ganymede's history, a collision with an asteroid or comet that released tremendous energy and reshaped the local landscape. By studying the distribution and characteristics of craters across Ganymede's surface, scientists can reconstruct the history of bombardment this moon has experienced and estimate the ages of different surface units. The composition of Ganymede's surface has been studied through spectroscopic observations, which analyze the light reflected from the surface to identify the materials present. These studies confirm that water ice dominates the surface composition, particularly in the bright terrain where fresh ice is exposed. The dark terrain contains a higher proportion of rocky material mixed with the ice, giving it its characteristic darker appearance. Various other compounds have been detected in smaller quantities, including carbon dioxide, sulfur dioxide, and possibly organic molecules. The distribution of these materials across Ganymede's surface is not uniform. Polar regions tend to be brighter than equatorial regions, possibly due to the migration of water molecules from warmer equatorial areas to colder polar cold traps. The leading hemisphere, which faces forward in the direction of Ganymede's orbital motion, shows different spectral characteristics than the trailing hemisphere, reflecting the different bombardment environments experienced by each side. Charged particles trapped in Jupiter's magnetosphere preferentially strike the trailing hemisphere, altering the surface chemistry through a process called radiolysis. Imagine standing on Ganymede's surface surrounded by this alien landscape. The ground beneath your feet would be hard as rock, water ice frozen to temperatures far below anything experienced on Earth. The horizon would curve noticeably closer than on Earth due to Ganymede's smaller size, giving the landscape an intimate quality despite its vast extent. Jupiter would dominate the sky if you stood on the subjovian hemisphere, a massive striped sphere hanging motionless overhead, its cloud bands and storms visible in exquisite detail. The sun would appear as a small but brilliant point, providing enough light to see clearly but little warmth to counter the bitter cold. Looking across the terrain, you might see the gentle undulations of grooved terrain stretching to the horizon, parallel ridges and troughs creating a corrugated texture that catches the dim sunlight at varying angles. In the distance, the rim of an impact crater might rise above the general surface level, a circular wall marking the site of an ancient collision. The colours would be subtle, shades of grey and brown with occasional brighter patches where fresh ice has been exposed. No atmosphere would soften the view or scatter the light, leaving the landscape in stark clarity beneath a black sky studded with stars. The surface features of Ganymede record a history spanning billions of years, from the ancient dark terrains that preserve the scars of the early solar system's violence to the younger grooved terrains that speak of internal geological activity. This history is written in a language of craters, grooves, and subtle colour variations, a language that scientists are still learning to read. Each new observation adds vocabulary to our understanding. Each spacecraft image reveals new sentences in the ongoing story of this remarkable world. As we continue our journey through Ganymede's story, we will descend beneath this frozen surface to explore the hidden interior, where liquid water may flow in a vast underground ocean, and a metallic core generates the only magnetic field possessed by any moon in our solar system. The surface features we have explored are merely the outermost layer of a complex world, a frozen shell concealing depths that may hold some of the most exciting discoveries in planetary science. Section 6. The Interior Layers of a Hidden World. Beneath the frozen landscapes we have just explored lies a world within a world, a complex interior structure that scientists have pieced together through decades of careful observation and analysis. Ganymede is not a uniform ball of ice and rock, but a differentiated body, meaning that its materials have separated into distinct layers based on their density. This layered structure tells the story of Ganymede's formation and evolution, revealing processes that occurred billions of years ago and continue to shape this moon today. The journey from Ganymede's surface to its centre would take us through approximately 2,634 kilometres of varied materials, each layer with its own composition, properties, and role in the moon's overall structure. This distance is substantial, roughly equivalent to travelling from New York to Los Angeles, yet it represents only the radius of this moon. The full diameter spans twice this distance, encompassing a volume large enough to contain every ocean, continent, and atmosphere of Earth with room to spare. At the very centre of Ganymede lies an iron-rich core, a dense metallic heart that distinguishes this moon from most other satellites in the solar system. This core is estimated to have a radius of approximately 500 to 700 kilometres, making it comparable in size to the entire moon of Earth. The core is composed primarily of iron, possibly mixed with iron sulfide, and exists at temperatures high enough to keep at least the outer portion in a liquid state. This liquid outer core is crucial for generating Ganymede's magnetic field, as we will explore in detail later. The existence of a metallic core within Ganymede was not always expected. Early models of the moon's interior assumed a relatively simple structure, with rock and ice mixed together in varying proportions. The discovery of Ganymede's magnetic field by the Galileo spacecraft in 1996 forced scientists to revise these models dramatically. A magnetic field of the type observed at Ganymede requires a dynamo mechanism, the circulation of electrically conducting fluid that generates magnetic fields through electromagnetic induction. On Earth, this dynamo operates in the liquid iron outer core, and the same process appears to be at work within Ganymede. The temperature at Ganymede's core is estimated to reach approximately 1,500 to 1,700 Kelvin, hot enough to keep iron in a molten state despite the tremendous pressures at such depths. This heat is a remnant of Ganymede's formation, when the gravitational energy of infalling material was converted to thermal energy, supplemented by the decay of radioactive elements within the rocky material. Over billions of years, this primordial heat has been slowly leaking away into space, but enough remains to maintain the liquid state of the outer core and drive the dynamo that generates the magnetic field. Surrounding the metallic core is a thick mantle of silicate rock, similar in composition to the rocky mantles of the terrestrial planets. This rocky layer extends from the outer boundary of the core to a radius of approximately 1,800 kilometres, giving it a thickness of roughly 100 to 1,300 kilometres. The silicate mantle contains the bulk of Ganymede's rocky material, including radioactive elements whose decay contributes to the moon's internal heat budget. The rocky mantle of Ganymede is not directly observable, hidden as it is beneath hundreds of kilometres of ice. Scientists infer its properties from measurements of Ganymede's total mass, its moment of inertia, and its response to tidal forces from Jupiter. These measurements constrain the distribution of mass within the moon, allowing researchers to construct models of the interior structure. The models consistently indicate a substantial rocky component concentrated toward the centre, overlain by less dense icy material. Above the silicate mantle begins the realm of ice, but this is not the simple frozen water we encounter on Earth. At the pressures found deep within Ganymede, water ice takes on exotic forms, quite different from the familiar ice that floats in our drinks. The phase diagram of water which maps the different forms water can take at various temperatures and pressures, reveals a surprising complexity. At least 17 different crystalline forms of ice have been identified in laboratory experiments, each stable under specific conditions of temperature and pressure. The ice layer immediately above Ganymede's rocky mantle likely consists of high-pressure ice phases, particularly Ice 6 and Ice 7. These exotic ices are denser than ordinary ice and form only under pressures exceeding about 600 megapascals, roughly 6,000 times Earth's atmospheric pressure. Ice 6 has a tetragonal crystal structure, while Ice 7 has a cubic structure. Both are significantly denser than the ice one that forms at Earth's surface, with densities approaching 1.3 grams per cubic centimetre compared to 0.92 grams per cubic centimetre for ordinary ice. The presence of these high-pressure ice phases has important implications for Ganymede's internal structure and the possibility of life in its subsurface ocean. Unlike ordinary ice, which floats on liquid water, high-pressure ices are denser than liquid water and would sink. This means that any ocean within Ganymede would be sandwiched between layers of ice, with ordinary ice above and high-pressure ice below. The ocean would not be in direct contact with the rocky mantle, potentially limiting the chemical exchanges that could provide nutrients and energy for life. The subsurface ocean of Ganymede represents one of the most exciting discoveries in planetary science. Evidence for this ocean comes from multiple sources, including measurements of Ganymede's magnetic field and its response to Jupiter's varying magnetic environment. The Hubble Space Telescope observed subtle oscillations in Ganymede's auroral belts, the glowing regions near the poles where charged particles interact with the thin atmosphere. These oscillations are best explained by the presence of a conducting layer beneath the surface, most likely a salty ocean of liquid water. The ocean is estimated to lie approximately 150 to 200 kilometers beneath Ganymede's surface, buried under a thick shell of ice one. Its depth remains uncertain, but models suggest it could be 100 kilometers deep or more, containing a volume of water that exceeds all the oceans of Earth combined. The salinity of this ocean is unknown, but it must contain enough dissolved salts to make it electrically conducting, allowing it to interact with Jupiter's magnetic field in the observed manner. The temperature of Ganymede's subsurface ocean would hover near the freezing point of water, perhaps a few degrees below 0 Celsius if the salt content is high enough to depress the freezing point. This is cold by earthly standards, but warm compared to the frigid surface temperatures. The ocean exists in a zone where the heat flowing outward from Ganymede's interior balances the cold seeping inward from the surface, maintaining a narrow band of liquid water within the otherwise frozen interior. Above the ocean lies the ice shell that forms Ganymede's outer layer, a frozen crust approximately 150 to 200 kilometers thick. This shell is composed primarily of ice one, the ordinary form of water ice familiar from Earth. The ice shell is not static but slowly convex, with warmer ice rising from the base of the shell and cooler ice sinking from the surface. This convection helps transport heat from the interior to the surface, where it radiates away into space. The surface features we explored earlier, the grooves and fractures that mark Ganymede's bright terrain, likely formed through processes occurring within this ice shell. As the shell convects and responds to stresses from the interior, it cracks and deforms, creating the tectonic features visible on the surface. The relationship between interior processes and surface geology is complex and not fully understood, but it is clear that Ganymede's surface is intimately connected to the dynamics of its icy interior. The total structure of Ganymede, from surface to centre, can be summarised as a series of concentric shells. At the centre lies the iron-rich core, partially liquid and generating the magnetic field. Surrounding this is the silicate mantle, a thick layer of rock containing radioactive heat sources. Above the rock comes a layer of high-pressure ice, dense exotic phases that form only under tremendous pressure. Then comes the subsurface ocean, a vast reservoir of liquid water sandwiched between ice layers. Finally, the outer ice shell forms the frozen surface we observe from space, bearing the scars of impacts and the grooves of ancient tectonic activity. This layered structure makes Ganymede one of the most complex moons in the solar system. The differentiation into distinct layers required significant heating early in Ganymede's history, enough to melt the ice and allow the denser rocky and metallic materials to sink toward the centre. This heating likely came from a combination of accretional energy released during Ganymede's formation and the decay of radioactive elements. The orbital resonance with Io and Europa may have also contributed tidal heating, though less intense than that experienced by the inner moons. The contrast with Callisto is instructive. Callisto, similar in size and composition to Ganymede, never fully differentiated into distinct layers. Its interior appears to be a relatively uniform mixture of rock and ice, only partially separated. The difference likely stems from Callisto's position outside the orbital resonance, which meant it experienced less tidal heating than Ganymede. Without sufficient heat to drive complete differentiation, Callisto remained in a more primitive state, preserving a record of conditions in the early outer solar system. Understanding Ganymede's interior structure is not merely an academic exercise. The presence of a subsurface ocean raises profound questions about the possibility of life beyond Earth. Liquid water is considered essential for life as we know it, and Ganymede possesses an ocean larger than all of Earth's oceans combined. The question is whether this ocean provides the other ingredients necessary for life: energy sources, chemical nutrients, and stable conditions over geological timescales. The separation of Ganymede's ocean from the rocky mantle by a layer of high-pressure ice complicates the picture. On Earth, hydrothermal vents on the ocean floor provide energy and nutrients that support thriving ecosystems in the deep sea. If Ganymede's ocean cannot interact directly with rock, these energy sources might be unavailable. However, some scientists have proposed that chemical exchanges could still occur through the high-pressure ice layer, or that other energy sources might be available within the ocean itself. The interior of Ganymede remains largely hidden from direct observation, its secrets buried beneath hundreds of kilometers of ice. Future missions will attempt to probe this hidden realm using various techniques, from radar sounding to precise measurements of the moon's gravitational field. Each new piece of data will help refine our models of Ganymede's interior, bringing us closer to understanding this complex and fascinating world. As we continue our exploration of Ganymede, we turn next to one of its most remarkable features: the magnetic field that makes this moon unique among all the satellites in our solar system. This invisible shield, generated deep within Ganymede's core, interacts with Jupiter's immense magnetosphere in complex ways, creating phenomena that scientists are still working to understand. The magnetic field provides a window into Ganymede's interior, revealing the presence of the liquid core that drives the dynamo, and hinting at the conducting ocean that lies beneath the frozen surface. The layers of Ganymede, from metallic core to icy surface, represent billions of years of planetary evolution compressed into a single world. Each layer tells part of the story, from the primordial heat that drove differentiation to the ongoing processes that maintain the subsurface ocean. Understanding these layers means understanding how worlds form and evolve, knowledge that extends far beyond Ganymede, to inform our understanding of planets and moons throughout the cosmos. Section 7. The Magnetic Mystery, Ganymede's unique field. In the vast catalogue of moons that orbit the planets of our solar system, numbering well over 200 confirmed satellites, only one possesses an internally generated magnetic field. That singular moon is Ganymede. This distinction makes Ganymede not merely the largest moon in the solar system, but also one of the most scientifically intriguing, a world that challenges our understanding of how magnetic fields form and persist in planetary bodies. The story of Ganymede's magnetic field is a tale of discovery, mystery, and ongoing investigation that continues to captivate scientists today. The discovery of Ganymede's magnetic field came as a profound surprise. When the Galileo spacecraft arrived at Jupiter in December 1995, scientists expected to find interesting phenomena at the giant planet and its moons. But few anticipated that a moon would possess its own intrinsic magnetosphere. The prevailing understanding held that magnetic field generation required specific conditions: a large body with a liquid, electrically conducting core that convects vigorously enough to sustain a dynamo. Moons, being generally smaller and cooler than planets, were not expected to meet these requirements. On June 27, 1996, the Galileo spacecraft made its first close flyby of Ganymede, passing within 835 kilometers of the moon's surface. The magnetometer aboard the spacecraft, an instrument designed to measure magnetic field strength and direction, recorded something unexpected. As Galileo approached Ganymede, the magnetic field measurements began to deviate from what would be expected if the moon were simply embedded in Jupiter's powerful magnetosphere. The data revealed a distinct magnetic signature emanating from Ganymede itself, a dipole field similar in structure to Earth's magnetic field, but much weaker. The initial measurements were tantalizing, but not conclusive. Scientists needed additional flybys to confirm the discovery and characterize the field in detail. Over the following years, Galileo made 6 close passes by Ganymede, each providing new data that refined our understanding of the moon's magnetic environment. The accumulated evidence left no doubt. Ganymede possesses an intrinsic magnetic field generated by processes within its interior, making it unique among all the moons in our solar system. The strength of Ganymede's magnetic field at its surface measures approximately 719 nanoteslas at the equator, roughly 1% of Earth's surface field strength of about 50,000 nanoteslas. While this may seem weak by terrestrial standards, it is strong enough to carve out a distinct magnetosphere within Jupiter's much larger magnetic domain. Ganymede's magnetosphere extends approximately 1 Ganymede radius above the surface on the side facing Jupiter and stretches into a tail on the opposite side, creating a bubble of magnetic influence embedded within the Jovian magnetosphere. The structure of Ganymede's magnetic field closely resembles a dipole, the same configuration as a simple bar magnet with north and south poles. The magnetic axis is tilted approximately 126 degrees relative to Ganymede's rotational axis, meaning that the magnetic poles are nearly aligned with the geographic poles, but with opposite polarity. If you could stand at Ganymede's north geographic pole, you would find yourself near the south magnetic pole, a configuration opposite to the current arrangement on Earth. The generation of this magnetic field requires a dynamo mechanism operating within Ganymede's interior. A planetary dynamo works through the motion of electrically conducting fluid, typically liquid iron or iron alloy, in the presence of an existing magnetic field. As the conducting fluid moves, it generates electric currents through electromagnetic induction. These currents, in turn, produce magnetic fields that reinforce and sustain the original field. The process is self-sustaining as long as the fluid continues to convect vigorously enough to overcome the natural decay of the magnetic field through electrical resistance. For Ganymede to possess a dynamo, it must have a liquid, electrically conducting layer in its interior. The most likely candidate is a liquid iron or iron-sulfur outer core, similar to Earth's liquid outer core. The presence of sulfur would lower the melting point of iron, making it easier to maintain a liquid layer at the relatively modest temperatures expected within Ganymede. Models of Ganymede's interior suggest that the outer portion of its metallic core remains liquid, providing the conducting fluid necessary for dynamo action. The persistence of Ganymede's dynamo over billions of years presents a puzzle. Dynamos require energy to drive the convection that generates the magnetic field. On Earth, this energy comes from two main sources: the gradual cooling of the core, which releases heat that drives convection, and the crystallization of the inner core, which releases latent heat and light elements that rise buoyantly through the outer core. Ganymede, being much smaller than Earth, would have cooled more rapidly, potentially exhausting these energy sources long ago. Several hypotheses have been proposed to explain how Ganymede's dynamo has survived. One possibility is that the core contains a significant fraction of sulfur or other light elements, which would lower the melting point and allow the core to remain partially liquid even at relatively low temperatures. Another possibility is that tidal heating from Ganymede's orbital resonance with Io and Europa provides an additional energy source, supplementing the heat from radioactive decay and primordial cooling. A third hypothesis suggests that Ganymede's dynamo may be relatively young, having started or restarted due to some event in the Moon's geological history. The interaction between Ganymede's magnetosphere and Jupiter's much larger magnetosphere creates a complex and dynamic environment. Jupiter possesses the most powerful magnetic field of any planet in our solar system, approximately 20,000 times stronger than Earth's field at the cloud tops. This immense magnetic domain extends millions of kilometers into space, engulfing all of Jupiter's major moons. Ganymede orbits entirely within Jupiter's magnetosphere, meaning that its own magnetic field must coexist with and interact with the Jovian field. Where Ganymede's magnetosphere meets Jupiter's magnetosphere, a boundary called the magnetopause forms. On the side of Ganymede facing Jupiter, the magnetopause lies relatively close to the surface, compressed by the pressure of Jupiter's magnetic field. On the opposite side, Ganymede's field is stretched into a magnetotail that extends away from Jupiter, similar to the way Earth's magnetosphere is stretched into a tail by the solar wind. The geometry of this interaction changes as Ganymede orbits Jupiter, with the Moon experiencing different orientations relative to the Jovian magnetic field at different points in its orbit. Charged particles trapped in Jupiter's magnetosphere constantly bombard Ganymede, but the Moon's magnetic field provides partial protection. Particles approaching Ganymede are deflected by the magnetic field, channeled toward the polar regions where the field lines converge. This focusing of charged particles toward the poles creates auroral phenomena, glowing regions where the particles interact with Ganymede's thin atmosphere. These auroras have been observed by the Hubble Space Telescope, appearing as faint ultraviolet emissions near the Moon's poles. The auroral observations have proven invaluable for understanding Ganymede's interior structure. Scientists noticed that the auroral belts rock back and forth as Ganymede orbits Jupiter, responding to changes in the orientation of Jupiter's magnetic field. However, the amount of rocking is less than would be expected if Ganymede's interior were entirely solid. The reduced rocking suggests the presence of a conducting layer beneath the surface that partially shields the interior from Jupiter's varying field. This conducting layer is most likely the subsurface ocean of salty water that we discussed earlier. The connection between Ganymede's magnetic field and its subsurface ocean illustrates how different aspects of planetary science interrelate. The magnetic field, generated deep in the metallic core, interacts with Jupiter's magnetosphere to create auroras in the thin atmosphere. The behavior of these auroras reveals the presence of a conducting ocean buried beneath the ice shell. Each observation provides a piece of the puzzle, and together they paint a picture of a complex layered world with active processes occurring at multiple depths. The uniqueness of Ganymede's magnetic field among moons raises questions about why other large satellites lack similar fields. Callisto, nearly the same size as Ganymede, shows no evidence of an intrinsic magnetic field. The difference likely relates to Callisto's incomplete differentiation, which means it may lack a distinct metallic core capable of generating a dynamo. Titan, Saturn's largest moon, and the second largest moon in the solar system, also lacks an intrinsic field, possibly because its interior has cooled too much to sustain dynamo action. Europa and Io, the other Galilean moons, also lack intrinsic magnetic fields, though for different reasons. Io experiences such intense tidal heating that its interior may be too hot and too thoroughly mixed to maintain a stable dynamo. Europa's smaller size means it would have cooled more rapidly than Ganymede, potentially solidifying any metallic core that might have existed. The specific combination of size, composition, and thermal history that allows Ganymede to maintain its dynamo appears to be relatively rare among moons. The study of Ganymede's magnetic field continues to be an active area of research. Future missions, particularly the European Space Agency's Zeus spacecraft, will carry sophisticated magnetometers capable of mapping the field in unprecedented detail. These measurements will help scientists understand the structure of Ganymede's core, the nature of the dynamo mechanism, and the properties of the subsurface ocean. Each new piece of data will refine our models and deepen our understanding of this remarkable moon. The magnetic field of Ganymede represents more than a scientific curiosity. It demonstrates that the processes we associate with planets, the generation of magnetic fields through core dynamos, can occur in moons under the right conditions. This finding expands our understanding of what is possible in planetary science, suggesting that the diversity of worlds in our universe may be even greater than we imagined. Ganymede's magnetic field is a reminder that nature often surprises us, revealing phenomena we did not expect in places we did not anticipate. As we rest in the contemplation of Ganymede's magnetic mysteries, we can appreciate the invisible forces that shape this distant world. The magnetic field lines that arc from pole to pole, the auroras that glow faintly in the thin atmosphere, the dynamo churning deep within the metallic core, all of these phenomena occur in silence and darkness, far from human eyes, yet they are no less real and no less wondrous for being unseen. The magnetic field of Ganymede connects the moon's deepest interior to the space environment around it, a thread of invisible force linking core to cosmos. Section 8. The tenuous atmosphere. When we think of atmospheres, we typically imagine the thick blanket of gases that surrounds Earth, the air we breathe, the medium through which clouds drift and winds blow. By this standard, Ganymede barely possesses an atmosphere at all. The gases surrounding this moon are so sparse that they would qualify as a laboratory vacuum by earthly standards. Yet this tenuous envelope of molecules, thin as it is, reveals important information about Ganymede's surface processes and its interaction with the space environment. The atmosphere of Ganymede is a whisper of gas in the void, but even whispers can tell stories. The existence of an atmosphere around Ganymede was first confirmed in 1972 when astronomers detected evidence of atomic hydrogen surrounding the Moon. Subsequent observations revealed the presence of oxygen, and later studies identified additional components, including ozone and possibly hydrogen peroxide. The total atmospheric pressure at Ganymede's surface is estimated at roughly 1/1,000,000th of Earth's sea level pressure, so low that individual molecules travel vast distances between collisions. This type of atmosphere is called an exosphere, a region where gas molecules are so sparse that they follow ballistic trajectories rather than behaving as a continuous fluid. The primary component of Ganymede's atmosphere is molecular oxygen. Two oxygen atoms bonded together in the same configuration as the oxygen we breathe on Earth. However, the oxygen in Ganymede's atmosphere did not arise through biological processes as it did on our planet. Instead, it forms through a purely physical mechanism involving the interaction of radiation with the icy surface. This process, called radiolysis, breaks apart water molecules and releases oxygen into the thin atmosphere. Radiolysis occurs when energetic particles or photons strike water ice and deposit enough energy to break the chemical bonds holding water molecules together. On Ganymede, the primary agents of radiolysis are charged particles trapped in Jupiter's magnetosphere and ultraviolet radiation from the Sun. When these energetic particles and photons impact the icy surface, they shatter water molecules into their constituent atoms. The hydrogen atoms, being light, escape readily into space, while the heavier oxygen atoms remain behind, gradually accumulating to form the tenuous oxygen atmosphere. The rate of oxygen production through radiolysis depends on several factors, including the intensity of the radiation striking the surface and the properties of the ice itself. Ganymede's position within Jupiter's magnetosphere exposes it to a constant flux of charged particles, though the Moon's own magnetic field provides some protection. The trailing hemisphere of Ganymede, which faces into the flow of corrotating plasma in Jupiter's magnetosphere, receives more intense particle bombardment than the leading hemisphere. This asymmetry may lead to differences in atmospheric density between the two hemispheres. In addition to radiolysis, another process contributes to Ganymede's atmosphere: sublimation. When sunlight warms the icy surface, some water molecules gain enough energy to escape directly from the solid ice into the gas phase, bypassing the liquid state entirely. This process is most effective in the warmer equatorial regions during local daytime, when surface temperatures can reach approximately 110 Kelvin. The sublimated water vapour adds to the atmospheric inventory, though much of it quickly freezes back onto the surface or escapes into space. The balance between production and loss determines the density of Ganymede's atmosphere at any given time and location. Molecules are constantly being added through radiolysis and sublimation, while simultaneously being lost through various mechanisms. Thermal escape occurs when molecules in the high-energy tail of the velocity distribution move fast enough to overcome Ganymede's gravity and fly off into space. Sputtering, the ejection of surface molecules by impacting charged particles, also removes material from the atmosphere. Additionally, chemical reactions can transform atmospheric species into forms that are more easily lost or that condense back onto the surface. The detection of ozone in Ganymede's atmosphere added another dimension to our understanding of this tenuous gas envelope. Ozone consists of 3 oxygen atoms bonded together, and on Earth it forms primarily through photochemical reactions in the stratosphere. On Ganymede, ozone likely forms through similar photochemical processes, with ultraviolet radiation driving reactions that combine oxygen molecules and atoms into ozone. The presence of ozone indicates that Ganymede's atmosphere, thin as it is, supports a rudimentary atmospheric chemistry. Observations by the Hubble Space Telescope have mapped the distribution of oxygen and ozone across Ganymede's surface and atmosphere. These studies reveal that the atmospheric density varies with location, being generally higher in the sunlit hemisphere, where sublimation is active, and in regions exposed to intense particle bombardment. The polar regions, where Ganymede's magnetic field channels charged particles toward the surface, may experience enhanced atmospheric production due to increased radiolysis. The interaction between Ganymede's atmosphere and its magnetic field creates interesting phenomena. Charged particles from Jupiter's magnetosphere that penetrate Ganymede's magnetosphere can ionize atmospheric molecules, creating a population of ions that interact with the magnetic field. These ions are picked up by the magnetic field and accelerated, contributing to the complex plasma environment around the Moon. The auroras observed near Ganymede's poles result from this interaction, as charged particles collide with atmospheric molecules and excite them to emit light. The atmospheric pressure on Ganymede varies not only with location, but also with time. As the Moon orbits Jupiter, different regions are exposed to sunlight and particle bombardment, causing the atmosphere to shift and change. During eclipse periods, when Ganymede passes through Jupiter's shadow, surface temperatures drop and sublimation decreases, potentially causing the atmosphere to partially collapse as molecules freeze onto the surface. When sunlight returns, the atmosphere regenerates as sublimation resumes. Comparing Ganymede's atmosphere to those of other moons in the solar system provides useful context. Europa, Ganymede's neighbour in the Jupiter system, also possesses a thin oxygen atmosphere produced by similar radiolytic processes. Callisto has an even more tenuous atmosphere, primarily composed of carbon dioxide. Titan, Saturn's largest moon, stands in stark contrast with its thick nitrogen atmosphere and complex organic chemistry. Triton, Neptune's largest moon, has a thin atmosphere of nitrogen and methane. Each of these atmospheres reflects the unique conditions and processes operating on its respective world. The study of Ganymede's atmosphere contributes to our broader understanding of atmospheric processes throughout the solar system. The mechanisms that produce and maintain this tenuous gas envelope, radiolysis, sublimation, photochemistry, and escape, operate on many icy bodies in the outer solar system. By studying these processes on Ganymede, scientists gain insights applicable to Europa, Enceladus, Triton, and potentially countless other icy worlds orbiting distant stars. Future missions will provide more detailed measurements of Ganymede's atmosphere. The Zeus spacecraft, scheduled to arrive at Jupiter in the 2030s, carries instruments capable of analysing the composition and structure of the atmosphere with unprecedented precision. These measurements will help scientists understand the sources and sinks of atmospheric molecules, the role of the magnetic field in shaping the atmosphere, and the connections between surface processes and atmospheric phenomena. Imagine standing on Ganymede's surface, surrounded by this almost imperceptible atmosphere. You would not feel any wind, for the gas is far too thin to exert noticeable pressure. You would not see any haze or colour in the sky, for there are not enough molecules to scatter light. The sky would appear black even during the day, with stars visible alongside the distant sun. Yet molecules of oxygen would surround you, invisible and sparse, a ghostly presence linking the icy surface to the space beyond. The atmosphere of Ganymede reminds us that the boundary between a world and space is not always sharp and clear. Even in the near vacuum surrounding this moon, processes continue that connect surface to sky, ice to gas, solid to void. The thin envelope of molecules that clings to Ganymede is a testament to the ongoing activity of this world, evidence that, even in the frozen outer reaches of the solar system, change and process never entirely cease. As we continue our journey through the story of Ganymede, we turn next to the history of human exploration of this distant moon. From the first crude images returned by Pioneer spacecraft to the detailed observations of the Galileo mission, our knowledge of Ganymede has grown through decades of robotic exploration. Each mission has revealed new wonders and raised new questions, driving us to send ever more sophisticated spacecraft to unravel the mysteries of this remarkable world. Section 9, Exploration History, Humanity's Visits to Ganymede. The story of human exploration of Ganymede spans more than 5 decades, a journey of discovery that has transformed this distant moon from a point of light in a telescope to a complex world with its own geology, interior structure, and potential for harbouring life. Each spacecraft that has visited the Jupiter system has added new chapters to our understanding, revealing details that previous generations of astronomers could scarcely have imagined. This is the story of how humanity reached out across the vast gulf of space to touch Ganymede with robotic eyes and instruments. The first spacecraft to venture into the outer solar system were Pioneer 10 and Pioneer 11, hardy probes launched by NASA in 1972 and 1973 respectively. These missions were designed primarily to study Jupiter itself, but they also provided humanity's first close-up glimpses of the Galilean moons. Pioneer 10 flew past Jupiter in December 1973, passing within about 130,000 kilometres of Ganymede. The images returned were crude by later standards, showing Ganymede as a fuzzy disk with hints of surface markings, but they represented a quantum leap beyond anything achievable from Earth. Pioneer 11 followed in December 1974, taking a different trajectory through the Jupiter system on its way to Saturn. This spacecraft also captured images of Ganymede, adding to the limited dataset from its predecessor. Together, the Pioneer missions demonstrated that the outer solar system was accessible to robotic exploration and paved the way for more ambitious missions to follow. They confirmed that Ganymede was a substantial world with a varied surface, though the resolution of their images was insufficient to reveal the detailed geology that later missions would uncover. The true revolution in our understanding of Ganymede came with the Voyager missions. Voyager 1 and Voyager 2, launched in 1977, were far more capable than the Pioneer spacecraft, carrying sophisticated cameras and instruments that would return data of unprecedented quality. These twin spacecraft took advantage of a rare alignment of the outer planets that occurs only once every 176 years, allowing them to visit multiple planets using gravity assists to bend their trajectories from one target to the next. Voyager 1 reached Jupiter in March 1979, passing within 115,000 kilometres of Ganymede. The images it returned transformed our view of this moon completely. For the first time, scientists could see the distinctive two-toned surface of Ganymede, with its dark ancient terrain and bright grooved regions. The resolution was good enough to reveal individual craters, groove systems, and the sharp boundaries between different terrain types. Ganymede emerged as a geologically complex world, far more interesting than the simple icy sphere many had expected. Voyager 2 arrived at Jupiter 4 months later, in July 1979, providing additional coverage of Ganymede and the other Galilean moons. The two spacecraft imaged different portions of Ganymede's surface, and together they provided nearly complete coverage of the moon at moderate resolution. Scientists pored over these images, mapping surface features and developing the first comprehensive geological interpretations of Ganymede's history. The grooved terrain was recognized as evidence of past tectonic activity, while the dark terrain was understood to represent ancient crust preserved from the early solar system. The Voyager encounters with Ganymede lasted only hours. brief flybys during which the spacecraft collected as much data as possible before continuing on their journeys to the outer solar system and beyond. Despite the brevity of these encounters, the data returned revolutionized our understanding of Ganymede. Scientists identified the major terrain types, catalogued hundreds of impact craters, mapped the distribution of grooved terrain, and began to piece together the geological history of this remarkable moon. Following the Voyager flybys, planetary scientists hungered for more detailed observations of the Jupiter system. The brief encounters had revealed tantalizing hints of complex geology and active processes, but many questions remained unanswered. What drove the formation of the grooved terrain? What lay beneath Ganymede's icy surface? Was there any possibility of liquid water or conditions suitable for life? Answering these questions would require a dedicated mission that could spend extended time in the Jupiter system, making repeated close passes of the major moons. The Galileo mission was designed to fulfill this need. Named in honor of the astronomer who first observed Jupiter's moons nearly 4 centuries earlier, Galileo was an ambitious spacecraft designed to orbit Jupiter and conduct detailed studies of the planet and its satellites. The mission faced numerous challenges during its development, including budget constraints, technical difficulties, and the tragic loss of the Space Shuttle Challenger in 1986, which delayed the launch. Finally, on October 18, 1989, Galileo lifted off from Kennedy Space Center aboard the Space Shuttle Atlantis. The journey to Jupiter took 6 years, with Galileo using gravity assists from Venus and Earth to gain the velocity needed to reach the outer solar system. During this long cruise, the spacecraft encountered an unexpected problem. The high-gain antenna, designed to transmit large volumes of data back to Earth, failed to fully deploy. Engineers worked tirelessly to find solutions, eventually developing techniques to maximize the data return using the low-gain antenna. While this limitation reduced the total amount of data Galileo could transmit, the mission still achieved remarkable scientific success. Galileo arrived at Jupiter in December 1995, becoming the first spacecraft to enter orbit around an outer planet. Over the following 8 years, the spacecraft made dozens of orbits around Jupiter, repeatedly passing close to the Galilean moons. Ganymede was a primary target, and Galileo made 6 close flybys of this moon between 1996 and 2000. The closest approach brought the spacecraft within just 264 kilometers of Ganymede's surface, close enough to image features as small as a few tens of meters across. The discoveries made during these flybys transformed our understanding of Ganymede. The most surprising finding was the detection of Ganymede's intrinsic magnetic field during the first flyby on June 27, 1996. As we discussed earlier, this discovery made Ganymede unique among all the moons in the solar system and implied the existence of a liquid metallic core capable of generating a dynamo. The magnetic field measurements also provided indirect evidence for a subsurface ocean, as the field's interaction with Jupiter's magnetosphere suggested the presence of a conducting layer beneath the surface. The high-resolution images returned by Galileo revealed the surface of Ganymede in unprecedented detail. Scientists could now see individual grooves within the grooved terrain, measuring their widths, depths, and spacing. Craters were imaged at resolution sufficient to study their internal structure, including central peaks, terraced walls, and ejecta blankets. The boundaries between dark and bright terrain were mapped in detail, revealing the complex relationships between different geological units. One of the most significant findings from the Galileo imaging data was evidence for cryovolcanism, volcanic activity involving water or other volatiles rather than molten rock. Some regions of Ganymede's surface showed smooth plains that appeared to have been flooded by liquid water that subsequently froze. Other areas displayed features suggestive of water erupting onto the surface and flowing before solidifying. While the evidence for cryovolcanism remains debated, it suggests that Ganymede's geological history may have included episodes of water reaching the surface from the interior. The Galileo mission also carried instruments to study Ganymede's composition. Spectrometers analysed the light reflected from the surface, identifying water ice as the dominant surface material and detecting various impurities, including carbon dioxide, sulfur dioxide, and possibly organic compounds. These compositional measurements helped scientists understand the processes that have shaped Ganymede's surface over billions of years, from the original formation of the Moon to the ongoing effects of radiation and micrometeorite bombardment. The mission concluded in September 2003 when Galileo was deliberately plunged into Jupiter's atmosphere to prevent any possibility of contaminating the potentially habitable moons with earthly microbes. By that time, the spacecraft had far exceeded its original mission duration and had returned a wealth of data that scientists are still analysing today. The legacy of Galileo includes not only the specific discoveries about Ganymede, but also the demonstration that extended orbital missions to the outer planets are feasible and scientifically valuable. Following the end of the Galileo mission, no spacecraft visited Ganymede for many years. However, observations continued from Earth-based telescopes and from spacecraft in other parts of the solar system. The Hubble Space Telescope made important contributions, including the detection of auroral activity on Ganymede that provided additional evidence for the subsurface ocean. Ground-based observatories with adaptive optics systems captured images approaching the quality of spacecraft data, tracking changes on Ganymede's surface over time. The Juno spacecraft, which arrived at Jupiter in July 2016, was designed primarily to study Jupiter itself rather than its moons. However, the mission has included several flybys of the Galilean moons, including a close pass by Ganymede on June 7, 2021. During this flyby, Juno approached within 1,038 kilometers of Ganymede's surface. The closest any spacecraft had come since Galileo's final flyby in 2000. The images and data returned provided new views of regions not well covered by previous missions, and demonstrated that Ganymede remains an active target of scientific interest. The Juno flyby of Ganymede captured stunning images of the Moon's surface, including detailed views of craters, grooved terrain, and the boundary between dark and bright regions. The spacecraft's instruments measured the radiation environment near Ganymede, studied the Moon's thin atmosphere, and probed the interaction between Ganymede's magnetosphere and Jupiter's magnetic field. While the encounter lasted only about 25 minutes, it added valuable new data to our understanding of this remarkable moon. Looking back over the history of Ganymede exploration, we can trace a progression from distant glimpses to intimate portraits. The Pioneer spacecraft showed us that Ganymede was a real world with surface features. The Voyager missions revealed the basic geology of the Moon, identifying the major terrain types and beginning the work of geological interpretation. The Galileo mission transformed our understanding completely, discovering the magnetic field, providing evidence for the subsurface ocean, and imaging the surface in exquisite detail. The Juno flyby demonstrated continued interest and added new pieces to the puzzle. Each mission built on the discoveries of its predecessors, answering some questions while raising new ones. The progression reflects not only advances in spacecraft technology, but also the growing sophistication of planetary science as a discipline. Early missions focused on basic reconnaissance, simply seeing what was there. Later missions could ask more specific questions, designing observations to test hypotheses and investigate particular phenomena. Future missions will continue this progression, probing ever deeper into Ganymede's mysteries. The human effort behind these missions deserves recognition. Thousands of scientists, engineers, technicians, and administrators have contributed to the exploration of Ganymede over the decades. They designed and built the spacecraft, planned the trajectories and observation sequences, operated the missions through years of flight, and analysed the data to extract scientific understanding. The images and measurements we have of Ganymede represent not just technological achievement, but human curiosity and determination, the drive to understand our universe that has characterized our species throughout history. As we look to the future, new missions are being prepared to continue the exploration of Ganymede. The next major chapter in this story will be written by the Zeus spacecraft, which we will discuss in detail later. But even as we anticipate future discoveries, we can appreciate how far we have come. From Galileo's first telescopic observations to the detailed spacecraft data we possess today, our understanding of Ganymede has grown immeasurably. This growth reflects the power of scientific exploration to reveal the wonders of the cosmos, one mission at a time. Section 10. The Ocean World, Astrobiology and the Search for Life. Among all the discoveries made about Ganymede over the decades of exploration, none captures the imagination quite like the presence of a vast subsurface ocean. Hidden beneath hundreds of kilometers of ice, this liquid water reservoir represents one of the largest potential habitats for life in our solar system. The possibility that living organisms might exist within Ganymede's dark ocean raises profound questions about the nature of life, its distribution in the universe, and our place in the cosmic order. This is the story of Ganymede as an ocean world and its significance for the search for life beyond Earth. The concept of ocean worlds has transformed our understanding of where life might exist in the universe. For most of human history, we assumed that life required conditions similar to those on Earth's surface, liquid water under an atmosphere, warmed by the nearby light of a star. This assumption placed strict limits on the habitable zone around any star, the narrow band of orbital distances where surface temperatures would allow liquid water to exist. Planets too close to their star would be too hot, their water boiled away. Planets too far would be too cold, their water frozen solid. The discovery of subsurface oceans on moons in the outer solar system shattered this limited view. Europa, Enceladus, and Ganymede demonstrated that liquid water could exist far beyond the traditional habitable zone, maintained not by stellar radiation, but by internal heat sources, such as tidal heating and radioactive decay. These worlds expanded the potential territory for life enormously, suggesting that habitable environments might be common throughout the galaxy, hidden beneath the icy surfaces of countless moons and dwarf planets. Ganymede's ocean was first suspected based on theoretical models of the moon's interior. Scientists recognized that a body of Ganymede's size and composition would have experienced significant heating during its formation and early evolution. This heat, combined with ongoing contributions from radioactive decay and tidal interaction with Jupiter, might be sufficient to maintain a layer of liquid water beneath the ice shell. The models were suggestive, but not conclusive, and direct evidence was needed to confirm the ocean's existence. The evidence came from multiple sources, each providing a different perspective on Ganymede's interior. The Galileo spacecraft's measurements of Ganymede's magnetic field and its interaction with Jupiter's magnetosphere suggested the presence of a conducting layer beneath the surface. The most likely explanation for this conducting layer was a salty ocean, since dissolved salts would make the water electrically conductive. The magnetic data alone did not prove the ocean's existence, but they were consistent with the theoretical predictions. More compelling evidence came from observations by the Hubble Space Telescope in 2015. Scientists used Hubble to study the auroral belts near Ganymede's poles, regions where charged particles interact with the thin atmosphere to produce faint ultraviolet emissions. These auroral belts rock back and forth as Ganymede orbits Jupiter, responding to changes in the orientation of Jupiter's magnetic field. However, the amount of rocking observed was less than would be expected if Ganymede's interior were entirely solid. The reduced auroral rocking indicated that something inside Ganymede was partially shielding the interior from Jupiter's varying magnetic field. A subsurface ocean of salty water would produce exactly this effect, generating induced magnetic fields that counteract the changes in Jupiter's field. By measuring the auroral oscillations precisely, scientists could estimate the depth and conductivity of the ocean. The results suggested an ocean approximately 100 kilometers deep, buried beneath an ice shell roughly 150 kilometers thick. The volume of water in Ganymede's ocean staggers the imagination. If the estimates are correct, this single moon contains more liquid water than all the oceans of Earth combined. The Pacific Ocean, the largest body of water on our planet, would be a mere puddle compared to Ganymede's hidden sea. This vast reservoir represents an enormous potential habitat, a space where life could potentially arise and evolve in isolation from the rest of the solar system. However, the existence of liquid water is only one requirement for life as we understand it. Living organisms also need energy sources to power their metabolism and chemical nutrients to build their bodies. On Earth, most life ultimately depends on energy from the sun, either directly through photosynthesis or indirectly by consuming organisms that photosynthesize. In the permanent darkness of Ganymede's ocean, sunlight is not available, and life would need to rely on alternative energy sources. One potential energy source is chemical disequilibrium, the presence of chemical compounds that can react to release energy. On Earth, ecosystems around deep-sea hydrothermal vents thrive on chemical energy rather than sunlight. These vents release hot, mineral-rich water from beneath the seafloor, creating environments where bacteria can harvest energy from chemical reactions. Similar processes might occur on Ganymede if hydrothermal activity exists on the ocean floor. Here we encounter one of the key uncertainties about life in Ganymede's ocean. Unlike Europa, where the ocean is believed to be in direct contact with a rocky seafloor, Ganymede's ocean may be sandwiched between layers of ice. Models of Ganymede's interior suggest that high-pressure ice phases, denser than liquid water, may form a layer beneath the ocean, separating the liquid water from the rocky mantle below. This configuration would limit the potential for hydrothermal activity and reduce the availability of chemical nutrients from rock-water interactions. The presence of a high-pressure ice layer between the ocean and the rocky interior does not necessarily preclude life, but it does complicate the picture. Some scientists have proposed that chemical exchanges could still occur across the ice layer, perhaps through slow diffusion or through localized melting and refreezing. Others have suggested that energy sources might exist within the ocean itself, independent of interactions with rock. Radiolysis of water by radiation penetrating from the surface could produce oxidants that diffuse downward into the ocean, potentially providing chemical energy for life. The question of nutrients is equally important. Life requires elements such as carbon, nitrogen, phosphorus, and sulfur to build the complex molecules that make up cells. On Earth, these elements are cycled between the atmosphere, oceans, and rocks through geological and biological processes. On Ganymede, the isolation of the ocean from both the surface and the rocky interior might limit the availability of essential nutrients. Without a continuous supply of these elements, any life in the ocean might struggle to sustain itself over geological timescales. Despite these challenges, the possibility of life in Ganymede's ocean cannot be dismissed. Life on Earth has proven remarkably adaptable, thriving in environments once thought too extreme to support living organisms. Microbes have been found in boiling hot springs, frozen Antarctic ice, highly acidic mine drainage, and rocks kilometers beneath Earth's surface. The limits of life are broader than we once imagined, and conditions that seem hostile by human standards might be perfectly acceptable for microbial organisms. If life does exist in Ganymede's ocean, it would almost certainly be microbial. The energy limitations of the environment would make it difficult to support large, complex organisms with high metabolic demands. Single-celled organisms, similar to bacteria or archaea on Earth, would be far more likely inhabitants. These microbes might form sparse communities scattered throughout the ocean, or they might concentrate in localized environments where energy and nutrients are more abundant. Detecting life in Ganymede's ocean presents formidable challenges. The ocean is buried beneath approximately 150 kilometers of ice, far beyond the reach of any drilling technology we currently possess. Even if we could somehow penetrate the ice shell, the sheer depth of the ocean would make exploration extremely difficult. Any mission to search for life in Ganymede's ocean would need to overcome engineering challenges that dwarf anything attempted in space exploration to date. One potential approach is to search for signs of life that have made their way to the surface. If material from the ocean occasionally reaches the surface through geological processes, it might carry biosignatures, chemical or physical traces of biological activity. These biosignatures could potentially be detected by spacecraft instruments without the need to penetrate the ice shell. However, the thick ice shell on Ganymede makes it less likely that ocean material reaches the surface compared to Europa, where the thinner ice shell may allow more exchange between ocean and surface. Another approach is to study the composition of Ganymede's thin atmosphere and any plumes of material that might be ejected from the surface. On Enceladus, Saturn's small icy moon, geysers of water vapour and ice particles erupt from the South Polar region, providing direct samples of the subsurface ocean. If similar plumes exist on Ganymede, they could offer a window into the ocean's composition without requiring a landing mission. However, no plumes have been definitively detected on Ganymede to date, though the search continues. The astrobiological significance of Ganymede extends beyond the specific question of whether life exists there. Ganymede serves as a natural laboratory for understanding the conditions necessary for habitability. By studying the moon's ocean, its chemistry, and its energy sources, scientists can refine their understanding of what makes an environment suitable for life. This knowledge applies not only to Ganymede, but to ocean worlds throughout the solar system and beyond. The comparison between Ganymede and Europa is particularly instructive. Both moons possess subsurface oceans, but their configurations differ in important ways. Europa's ocean appears to be in direct contact with rock, potentially allowing for hydrothermal activity and robust chemical cycling. Ganymede's ocean may be isolated from rock by high-pressure ice, limiting these processes. By comparing the two moons, scientists can assess the relative importance of different factors for habitability. Ganymede also provides a point of comparison for understanding ocean worlds around other stars. As astronomers discover more and more exoplanets, including many that may be icy worlds with subsurface oceans, the lessons learned from Ganymede will help interpret these distant discoveries. The principles that govern habitability on Ganymede should apply throughout the universe, making this moon a valuable case study for astrobiology. The search for life in Ganymede's ocean is ultimately a search for answers to some of humanity's deepest questions. Are we alone in the universe? Is life a rare accident, confined to our small blue planet, or is it a common phenomenon that arises wherever conditions permit? The discovery of even microbial life on Ganymede would transform our understanding of our place in the cosmos, demonstrating that life can emerge independently in multiple locations within a single solar system. As we contemplate the dark waters of Ganymede's hidden ocean, we are reminded of the vastness and mystery of the universe we inhabit. Somewhere beneath hundreds of kilometers of ice, in permanent darkness and crushing pressure, liquid water flows in quantities beyond human comprehension. Whether that water harbours life remains unknown, a question that future generations may answer through continued exploration and discovery. For now, Ganymede's ocean remains one of the most tantalizing mysteries in our solar system, a world within a world, waiting to reveal its secrets. Section 11, Future Exploration, Zeus and Beyond. The story of Ganymede's exploration is far from complete. Even as we reflect on the discoveries made by past missions, new spacecraft are being prepared to continue the journey of discovery. The coming decades will bring unprecedented opportunities to study this remarkable moon, with missions designed specifically to investigate the questions raised by earlier exploration. The future of Ganymede exploration promises to be as exciting as its past, with the potential for discoveries that could transform our understanding of this world and its place in the solar system. The most ambitious mission currently underway is the Jupiter Icy Moons Explorer, known by its acronym JUICE. This flagship mission of the European Space Agency represents the most comprehensive effort ever undertaken to study the Galilean moons, with Ganymede as its primary target. JUICE launched successfully on April 14, 2023, beginning a journey that will take approximately 8 years to complete. The spacecraft is currently travelling through the inner solar system, using gravity assists from Earth and Venus to gradually build up the velocity needed to reach Jupiter. The trajectory of JUICE is a masterpiece of celestial mechanics, carefully designed to use the gravity of multiple planets to propel the spacecraft toward its distant destination. After launch, JUICE performed a flyby of the Earth-Moon system in August 2024, using our planet's gravity to bend its trajectory and increase its speed. Additional gravity assists from Venus and Earth will follow in the coming years, each one nudging the spacecraft onto a path that will eventually carry it to Jupiter. This complex series of maneuvers is necessary because no rocket currently available has the power to send a spacecraft directly to Jupiter with enough fuel remaining for the extensive orbital operations planned at the destination. The arrival of JUICE at Jupiter is scheduled for July 2031, approximately 8 years after launch. Upon arrival, the spacecraft will enter orbit around Jupiter and begin a series of flybys of the Galilean moons. The initial phase of the mission will include 2 flybys of Europa, providing valuable data on that moon's ice shell and potential habitability. JUICE will also make numerous flybys of Callisto, using that moon's gravity to shape its orbit and gather scientific data on the ancient cratered surface. The culmination of the JUICE mission will be its entry into orbit around Ganymede, planned for December 2034. This will make JUICE the first spacecraft ever to orbit a moon other than Earth's moon, a historic achievement that will enable unprecedented scientific investigations. The orbital phase around Ganymede is planned to last at least 9 months, during which the spacecraft will make detailed observations of the moon's surface, interior, atmosphere, and magnetic environment. The scientific instruments aboard JUICE have been carefully selected to address the key questions about Ganymede that remain unanswered. The spacecraft carries 10 state-of-the-art instruments, each designed to investigate specific aspects of the moon and its environment. Together, These instruments will provide the most comprehensive picture of Ganymede ever obtained, building on the discoveries of previous missions while opening new avenues of investigation. The Janus camera system will image Ganymede's surface at resolutions far exceeding anything achieved by previous missions. This optical camera will map the entire surface at high resolution, revealing details of geological features that are currently only glimpsed in limited areas. The images will allow scientists to study the grooved terrain in unprecedented detail, investigate the structure of impact craters, and search for evidence of recent geological activity. The camera will also capture images of Ganymede's thin atmosphere and any plumes of material that might be ejected from the surface. The MAGIS spectrometer will analyze the composition of Ganymede's surface by studying the light reflected at different wavelengths. This instrument will map the distribution of water ice, identify other surface materials such as salts and organic compounds, and investigate how surface composition varies between different geological units. The compositional data will help scientists understand the processes that have shaped Ganymede's surface over billions of years and may provide clues about the composition of the subsurface ocean. The Rime radar sounder represents one of the most exciting instruments on Zeus, capable of peering beneath Ganymede's surface to probe the structure of the ice shell. This radar will send radio waves into the ice and detect reflections from subsurface layers, potentially including the boundary between ice and liquid water. If successful, Rime will provide direct evidence for the depth and structure of Ganymede's ocean, confirming and refining the estimates derived from magnetic field measurements. The Gala laser altimeter will measure the topography of Ganymede's surface with extreme precision, creating detailed maps of elevation across the Moon. These measurements will reveal the shapes of geological features, the depths of craters, and the heights of ridges and scarps. The altimeter data will also be used to measure tidal deformation, the slight bulging of Ganymede's surface caused by Jupiter's gravitational pull. The amplitude of this tidal bulge depends on the internal structure of the Moon, including the presence and depth of the subsurface ocean. The JMAG magnetometer will map Ganymede's magnetic field in unprecedented detail, building on the discoveries made by the Galileo spacecraft. By measuring how the magnetic field varies across the surface and at different altitudes, scientists will be able to refine their models of the dynamo operating in Ganymede's core. The magnetometer will also study the interaction between Ganymede's magnetosphere and Jupiter's magnetic field, investigating the complex plasma environment around the Moon. Additional instruments will study Ganymede's thin atmosphere, measure the radiation environment, investigate the properties of dust particles in the vicinity of the Moon, and probe the gravitational field to constrain the internal structure. Together, this suite of instruments will address virtually every aspect of Ganymede's nature, from the surface to the core, from the atmosphere to the magnetosphere. The Zeus mission represents a collaboration among scientists and engineers from across Europe and around the world. The European Space Agency leads the mission, but contributions have come from many nations, including the United States, Japan, and Israel. This international cooperation reflects the global nature of space exploration and the shared human desire to understand our cosmic environment. The discoveries made by Zeus will belong to all of humanity, expanding our collective knowledge of the universe we inhabit. While Zeus focuses primarily on Ganymede, another major mission will provide complementary observations of the Jupiter system. NASA's Europa Clipper, launched in October 2024, is designed to make detailed studies of Europa, investigating that Moon's ice shell, ocean, and potential habitability. Although Europa is the primary target, Europa Clipper will also make observations of Ganymede during its flybys of the Jupiter system. These observations will complement the data from Zeus, providing additional perspectives on Ganymede's surface and environment. The Europa Clipper spacecraft carries a sophisticated suite of instruments, similar in many ways to those on Zeus. Cameras will image the surfaces of the Galilean moons, spectrometers will analyze their compositions, and radar will probe beneath their icy shells. The magnetometer and plasma instruments will study the magnetic and charged particle environments. By combining data from both missions, scientists will be able to compare Ganymede and Europa in unprecedented detail, understanding how these two ocean worlds differ and what factors control their habitability. Looking further into the future, planetary scientists have proposed even more ambitious missions to Ganymede and the other Galilean moons. One concept that has received considerable attention is a lander mission that would place a spacecraft directly on Ganymede's surface. Such a mission could conduct detailed analyses of surface materials, search for organic compounds and biosignatures, and deploy seismometers to study the moon's interior structure. The technical challenges of landing on Ganymede are substantial, but not insurmountable with current or near-future technology. An even more ambitious concept is a mission to penetrate Ganymede's ice shell and directly explore the subsurface ocean. Such a mission would require technologies that do not yet exist, including ice-penetrating probes capable of melting or drilling through hundreds of kilometers of ice, and autonomous submarines capable of operating in an alien ocean without real-time communication with Earth. While these concepts remain in the realm of science fiction for now, they represent the ultimate goal of Ganymede exploration: direct contact with the hidden ocean and the potential life it might contain. The exploration of Ganymede is also connected to broader questions about human expansion into the solar system. Some visionaries have proposed that Ganymede could eventually serve as a base for human operations in the outer solar system. The moon's substantial size, relatively stable surface, and potential water resources make it an attractive candidate for long-term human presence. The magnetic field, while weak, provides some protection from Jupiter's intense radiation belts, an important consideration for human health. Of course, establishing a human presence on Ganymede would require overcoming enormous challenges. The distance from Earth means that communication delays would make real-time control impossible, requiring a high degree of autonomy for any human outpost. The cold temperatures and lack of breathable atmosphere would necessitate enclosed habitats with life support systems. The radiation environment, while partially shielded by Ganymede's magnetic field, would still pose health risks requiring careful management. Despite these challenges, the dream of humans walking on Ganymede's icy surface continues to inspire those who envision a spacefaring future for our species. The timeline for future Ganymede exploration extends across decades. Zeus will arrive at Jupiter in 2031 and enter orbit around Ganymede in 2034, with primary mission operations continuing into 2035 or beyond. Europa Clipper will conduct its flybys of the Jupiter system throughout the 2030s. Analysis of the data from these missions will continue for years after the spacecraft cease operations, as scientists work to extract every bit of information from the observations. New missions may be proposed and developed based on the discoveries made, potentially launching in the 2040s or 2050s. Each step in this progression brings us closer to understanding Ganymede and its place in the solar system. The questions that drive exploration today about the ocean's depth and composition, about the possibility of life, about the geological history recorded in the surface, will eventually be answered, only to be replaced by new questions that we cannot yet anticipate. This is the nature of scientific exploration. Each discovery opens new horizons, revealing how much more there is to learn. As we contemplate the future of Ganymede exploration, we can appreciate the continuity that connects past, present, and future. Galileo's first glimpse of Jupiter's moons in 1610 set in motion a chain of discovery that continues to this day. The Pioneer and Voyager spacecraft of the 1970s revealed Ganymede as a complex world worthy of detailed study. The Galileo mission of the 1990s and 2000s transformed our understanding with discoveries of the magnetic field and evidence for the subsurface ocean. Zeus and Europa Clipper will write the next chapters in this ongoing story, and missions yet to be conceived will carry the story forward into the distant future. The exploration of Ganymede is ultimately an expression of human curiosity, our innate desire to understand the universe and our place within it. This curiosity has driven us to send robotic emissaries across billions of kilometers of space to develop technologies that would have seemed magical to previous generations, and to ask questions about worlds that our ancestors could barely imagine. The future of Ganymede exploration is bright, filled with promise and potential, a testament to the enduring human spirit of discovery. Section 12. Ganymede's place in the cosmos. Conclusion. As our journey through the story of Ganymede draws to a close, we find ourselves reflecting on all that we have learned about this remarkable moon. From ancient mythology to cutting-edge science, from the first telescopic observations to the robotic explorers of the space age, Ganymede has captured human imagination and challenged our understanding of what is possible in the universe. This final chapter brings together the threads of our narrative, considering what Ganymede means for our understanding of the cosmos and our place within it. Ganymede occupies a unique position in the hierarchy of worlds that make up our solar system. It is the largest moon, exceeding even the planet Mercury in size. It is the only moon with an internally generated magnetic field, evidence of a dynamic interior that continues to evolve billions of years after formation. It harbours a subsurface ocean larger than all the oceans of Earth combined, a vast reservoir of liquid water hidden beneath a shell of ancient ice. These superlatives make Ganymede not merely interesting, but extraordinary, a world that stands apart from all others. The story of Ganymede is, in many ways, the story of planetary science itself. Our understanding of this moon has grown in parallel with our understanding of the solar system as a whole. When Galileo first observed Jupiter's moons, he could not have imagined the complex worlds that his simple telescope had revealed. When the Voyager spacecraft flew past Ganymede, scientists were astonished by the geological diversity of the surface. When the Galileo mission discovered the magnetic field and evidence for the ocean, our conception of what moons could be was transformed forever. Each generation of scientists has built on the work of those who came before, asking new questions and developing new tools to answer them. This cumulative process of discovery is one of the great achievements of human civilization, a testament to our ability to learn, to grow, and to understand. The knowledge we have gained about Ganymede did not come easily or quickly. It required centuries of observation, decades of spacecraft development, and the dedicated efforts of thousands of individuals working toward a common goal. Ganymede teaches us important lessons about the formation and evolution of planetary bodies. The moon's differentiated interior, with its metallic core, rocky mantle, and icy shell, records the processes that occurred during and after formation. The heat generated by accretion and radioactive decay drove the separation of materials by density, creating the layered structure we observe today. The persistence of a liquid core and a subsurface ocean demonstrates that internal heat can be maintained over billions of years, even in a body far from the warmth of the sun. The comparison between Ganymede and its sibling moons illuminates the factors that control planetary evolution. Io, Europa, Ganymede, and Callisto formed from the same disk of material around Jupiter, yet they have evolved into dramatically different worlds. The key variable appears to be tidal heating, which depends on orbital position and resonance relationships. Io, closest to Jupiter and locked in the tightest resonance, experiences intense heating that drives continuous volcanic activity. Europa, slightly farther out, maintains a subsurface ocean in contact with rock. Ganymede, more distant still, has a complex interior with an ocean sandwiched between ice layers. Callisto, outside the resonance, remains largely undifferentiated and geologically inactive. These comparisons have implications far beyond the Jupiter system. Throughout the galaxy, giant planets likely host systems of moons similar to Jupiter's. The principles that govern the evolution of the Galilean moons should apply to these distant systems as well. By understanding Ganymede and its siblings, we gain insight into the diversity of worlds that may exist around other stars, including worlds that might harbour conditions suitable for life. The possibility of life in Ganymede's ocean connects this distant moon to one of the most profound questions humans have ever asked. Are we alone in the universe? For most of human history, this question was purely philosophical, beyond the reach of scientific investigation. Today, we have the tools to begin searching for answers. The discovery of subsurface oceans on Ganymede, Europa, and Enceladus has revealed potential habitats for life in unexpected places, expanding the territory where we might find living organisms. If life exists in Ganymede's ocean, it would represent an independent origin of life, separate from the origin that gave rise to all life on Earth. Such a discovery would demonstrate that life is not a unique accident, but a natural phenomenon that arises when conditions permit. The implications would be staggering, suggesting that life might be common throughout the universe, arising on countless worlds around countless stars. Even if Ganymede's ocean proves to be lifeless, the search itself advances our understanding of what conditions are necessary for life and where we should look for it. Ganymede also holds significance for the long-term future of humanity. As our species looks outward from Earth, considering the possibility of expanding into the solar system, moons like Ganymede represent potential destinations for exploration and perhaps eventual settlement. The water ice that covers Ganymede's surface could be converted into drinking water, breathable oxygen, and rocket fuel. The moon's substantial gravity, while less than Earth's, is enough to provide a sense of weight and orientation. The magnetic field offers partial protection from radiation. While the challenges of living on Ganymede would be immense, they are not insurmountable for a sufficiently advanced civilization. The dream of human presence on Ganymede may seem distant today, but so too did the dream of landing on Earth's moon seem distant to those who first gazed at it through telescopes. The progression from observation to exploration to habitation has occurred before and may occur again. The robotic missions we send to Ganymede today are the precursors of the human missions that may follow in future centuries. Each discovery we make brings that future a little closer, building the knowledge base that will eventually enable humans to walk on the icy surface of this distant world. As we conclude our journey through the story of Ganymede, let us take a moment to appreciate the wonder of this world. Imagine yourself floating in space above Ganymede, looking down at the grooved terrain stretching to the curved horizon. Jupiter hangs enormous in the sky, its bands and storms visible in exquisite detail. The sun appears as a small but brilliant point, casting long shadows across the icy landscape. Somewhere beneath your feet, hundreds of kilometers down, liquid water flows in an ocean larger than any on Earth, dark and cold and utterly alien. This world exists. It is not a fantasy or a speculation, but a real place, orbiting Jupiter at this very moment, keeping its secrets beneath a shell of ancient ice. The same laws of physics that govern our daily lives on Earth govern the processes occurring on Ganymede. The same elements that make up our bodies make up the ice and rock of this distant moon. We are connected to Ganymede by the fundamental unity of the cosmos, by the shared origin of all matter in the nuclear furnaces of ancient stars. The story of Ganymede is not finished. It continues with every observation made by telescopes on Earth, with every measurement returned by spacecraft in the Jupiter system, with every model developed by scientists working to understand this complex world. The story will continue with the arrival of Zeus and Europa Clipper, with the discoveries they will make and the questions they will raise. It will continue with missions yet to be conceived, technologies yet to be developed, and explorers yet to be born. We are privileged to live in an age when the story of Ganymede is being written, when each year brings new discoveries and new understanding. The generations that came before us could only wonder about the nature of Jupiter's moons. The generations that come after us will know far more than we do today. We stand at a particular moment in the unfolding story, able to look back at how far we have come and forward to how far we have yet to go. Let the story of Ganymede carry you now into peaceful rest. Let the images of grooved terrain and ancient craters, of hidden oceans and magnetic fields, of spacecraft journeying across the void, fill your mind as you drift towards sleep. The universe is vast and full of wonders, and Ganymede is one of the most wondrous of all. It waits in the darkness of the outer solar system, patient and eternal, ready to reveal its secrets to those who seek them. Thank you for joining me on this journey through the complete story of Ganymede. If you enjoyed this exploration of one of the solar system's most fascinating worlds, please consider liking this video and subscribing to the channel for more journeys through the cosmos. Your support helps make these deep dives into space science possible, and I am grateful for every viewer who shares this passion for understanding our universe. Until next time, rest well, dream of distant worlds, and remember that the same stars that shine down on you tonight also shine on Ganymede, connecting us all in the grand cosmic story of which we are a part. Good night, and may your dreams carry you to the frozen shores of that distant moon, where mysteries await and wonders never cease.